Imagine walking through the grand streets of Babylon over 4,000 years ago. The city was a hub of culture, innovation and learning. Towering ziggurats, these massive step-like temples, dominated the skyline reaching towards the heavens. But these weren't just impressive architectural feats, they were the very heart of Babylonian spirituality and science. For the people of Babylon, the night sky wasn't just about beautiful sight. It was a canvas filled with stories, divine messages and cosmic patterns waiting to be understood. Astronomy wasn't just a hobby or a scientific endeavor, it was deeply ingrained into their culture, religion and daily life. Babylonian priests, who were also the astronomers of their time, would climb to the top of the ziggurats to observe the stars more closely. They believed that the movements of celestial bodies were messages from the gods. Each planet, star and constellation held significance, influencing everything from agriculture to decisions made by kings. The positions of Venus, Mars and other planets were thought to predict events like floods, famines and even the outcomes of wars. Their dedication to watching the skies led to some incredible achievements. They were among the first to create detailed star maps and calendars based on astronomical observations. The Babylonians divided the sky into recognizable constellations and even developed an early form of the zodiac that we still reference today. Their ability to predict celestial events like eclipses was astounding for their time. But why was this so important to them? Well, life in ancient Mesopotamia was closely tied to the rhythms of nature. Knowing when the rivers would flood or when to plant and harvest crops was crucial. By observing the heavens, they sought guidance and understanding of the world around them. Astronomy helped them bring order to the chaos, offering a sense of control and connection to the divine. The Babylonians weren't just casual stargazers, they were pioneers, turning their eyes to the night sky with a purpose and passion that was truly groundbreaking. Imagine priests and scholars standing atop of towering ziggurats night after night, meticulously observing the stars and planets. They weren't simply admiring the beauty of the cosmos, they were systematically studying it, seeking patterns and meanings in the movements above. Their dedication led to one of their most remarkable achievements, the creation of detailed star catalogues. These were ancient celestial maps that recorded the positions and movements of heavenly bodies with surprising accuracy. One of the most famous of these is Mulapin tablets. Dating back to around 1000 BCE, these clay tablets are a treasure trove of astronomical knowledge. Inscribed with cuneiform script, they list stars and constellations, their rising and setting times, and even instructions for predicting celestial events. But the Mulapin tablets were just one part of their extensive work. The Babylonians also produced texts like Enuma, Anu and Lil, a massive collection of omens and observations that linked astronomical phenomena to events on Earth. They believed that the gods communicated through the movements in the sky, so keeping detailed records was essential for interpreting these divine messages. What's truly amazing is how accurate their observations were. Without the aid of telescopes or modern technology, they charted the paths of the Moon, the Sun and the 5 visible planets, Mercury, Venus, Mars, Jupiter and Saturn. They noticed that while most stars held fixed positions relative to each other, these planets wandered across the sky. In fact, the word planet comes from a Greek word meaning wanderer, a concept that Babylonians were already familiar with. Their star catalogues weren't just scientific records, they were practical tools. The Babylonians used them to predict celestial events like eclipses, which had significant religious and cultural importance. They developed mathematical methods to calculate the timing of these events, demonstrating an impressive understanding of astronomical cycles. These observations also had everyday applications. By tracking the positions of certain stars and constellations, they could determine the best times for planting and harvesting crops. For example, the rising of the star Sirius might signal the flooding of the rivers, an essential piece of information for an agrarian society. Their calendars were intertwined with their astronomical observations, guiding not just agriculture, but religious festivals and civic activities. Beyond the Mulapin tablets, many other artifacts have been discovered that showcase their astronomical prowess. Clay tablets with intricate carvings and writings reveal tables of lunar and solar data, planetary positions, and even corrections to previous observations. This indicates a continuous effort to refine and improve their knowledge over generations. It's important to appreciate the context of their work. The Babylonians didn't separate astronomy from astrology or religion. It was all part of a unified effort to understand the universe and their place in it. The sky was a canvas painted by the gods, and by studying it, they sought to decipher divine will and maintain harmony between the heavens and the earth. Their systematic approach set the stage for future astronomers. The meticulous records kept by the Babylonians were later studied and built upon by Greek astronomers like Hipparchus and Ptolemy. The legacy of their star catalogues can be traced through history, influencing astronomical methods and knowledge well into the modern era. Think about the dedication it took to create these catalogues. Night after night, year after year, observing, recording, and analyzing, all without the conveniences we take for granted today. Their achievements remind us of the incredible human capacity for curiosity and the pursuit of knowledge. One of the most fascinating achievements of the Babylonian astronomers is the development of the zodiac and their understanding of constellations. Imagine standing under the clear, star-studded skies of ancient Mesopotamia. Without the glow of modern city lights, the night sky would have been a breathtaking tapestry of twinkling stars and wandering planets. The Babylonians were among the first to systematically observe the heavens. They noticed that the sun, moon, and the planets moved along a specific path in the sky, which we now call the ecliptic. To make sense of these movements, they divided this path into 12 equal sections, each covering 30 degrees of the sky's 360-degree circle. Each section was assigned a constellation, forming what we now know as the zodiac. These 12 constellations weren't just random groupings of stars, they were deeply embedded in Babylonian mythology and culture. They included familiar figures like Taurus, the bull, Leo, the lion, Scorpius, the scorpion, Aquarius, the water bearer, and Pisces, the fish. Each constellation held its own stories and significance, often linked to gods, heroes, and legendary creatures. By mapping the sky this way, the Babylonians created a celestial calendar that was incredibly valuable for their society. Agriculture was the lifeblood of Babylonian civilization. Knowing when to plant and harvest crops was crucial for feeding their people. The movements of the constellations provided a reliable guide for their activities. When Taurus rose in the night sky, it signaled the beginning of spring, a time to start planting. The appearance of Scorpius marked the onset of hot, dry season, indicating it was time to harvest. Aquarius, associated with the water bearer, brought the rainy season, guiding farmers on irrigation needs. By aligning their farming practices with celestial calendar, the Babylonians could predict seasonal changes and plan accordingly. This close observation of the stars ensured their agricultural activities were in harmony with the natural rhythms of the earth. The constellations also played a vital role in Babylonian religion and rituals. They believed that the stars were dwelling places of their gods, and that celestial events were messages from the divine. They developed an early form of astrology where the position of the sun, moon, and the planets within the zodiac constellations were thought to influence events on Earth and individual destinies. Important religious festivals were scheduled according to the celestial events. For example, the rising of certain stars might indicate it was time to honor a specific deity. Unusual occurrences like eclipses or the appearance of comets within a constellation were seen as significant omens. Priests and astrologers would interpret these signs to advise kings and guide decisions on matters like war, construction, and lawmaking. This deep connection between the cosmos and daily life meant that astronomy wasn't just about studying the stars. It was an integral part of their spirituality and governance. The zodiac served as a bridge between heaven and earth, allowing the Babylonians to feel connected to the divine and to seek guidance from the celestial realm. What's also remarkable is how the Babylonian zodiac has influenced cultures across the world. Their system was later adopted and adapted by the Greeks and Romans, and it eventually evolved into the zodiac signs many people are familiar with today. By transforming the sky into a cosmic map filled with a meaning and purpose, the Babylonians not only advanced the field of astronomy, but also enriched their cultural heritage. Their innovative approach allowed them to track time, predict seasons, and seek insights into both earthly and spiritual matters. In essence, the Babylonians turned the night sky into a cosmic calendar and a canvas for storytelling. Their legacy reminds us of humanity's enduring fascination with the stars and our timeless quest to find meaning in the universe around us. Building on their knowledge of stars and constellations, the Babylonians turned their attention to the wandering lights in the sky, the planets. To them, these weren't just points of light. They were celestial beings with significant influence over earthly matters. The Babylonians had a keen eye for observing the planets and a remarkable ability to predict their movements long before the invention of telescopes or modern instruments. They closely watched the 5 visible planets: Mercury, Venus, Mars, Jupiter, and Saturn. These planets fascinated the Babylonians because, unlike the fixed stars, they moved against the backdrop of the night sky in complex ways. They called them mul, meaning stars, but recognized that they behaved differently. Imagine trying to track Mercury, which is only visible for a short time during sunrise or sunset, or observing the steady glow of Venus, the bright morning star or evening star. The Babylonians meticulously recorded when and where these planets appeared, their brightness, and how they moved. Over generations, they gathered enough data to notice patterns in these movements. One of the significant achievements was identifying the synodic periods of the planets, the time it takes for a planet to return to the same position in the night sky relative to the sun as seen from Earth. For example, Venus has a synodic period of about 584 days, and Mars has a synodic period of approximately 780 days. By understanding these periods, the Babylonians could predict when a planet would reappear in the night sky, disappear, or reach its greatest brightness. This was incredibly useful for both practical purposes and astrological interpretations. But they didn't stop there. The Babylonians also developed methods to predict lunar eclipses which occur when the Earth comes between the Sun and the Moon, casting a shadow on the Moon. Through careful observations, they discovered the Saros cycle, a period of about 18 years and 11 days after which eclipses repeat themselves. This knowledge allowed them to predict not just when an eclipse would happen, but also where it might be visible. Predicting eclipses was a big deal. Eclipses were seen as powerful omens, often associated with significant events or changes. Being able to forecast them gave the Babylonians a sense of control over the unknown and allowed priests to prepare rituals or advise the rulers accordingly. Their predictions weren't based on superstition alone. They used mathematical calculations derived from their observations. They employed arithmetic methods to model the motions of Moon and the planets, which was a significant step toward understanding celestial mechanics. For instance, they used what's now called the System A and the System B models. System A involved a step function to predict planetary positions, and System B used zigzag functions to account for variations in speed. These mathematical models were surprisingly accurate for their time and demonstrated an advanced understanding of how celestial bodies moved. The Babylonians' ability to predict planetary positions also had practical implications. Certain planetary movements were linked to favorable or unfavorable conditions for planting and harvesting. Knowing the positions of planets helped the nighttime navigation both on land and the sea. Kings and leaders sought guidance based on planetary positions, affecting decisions on warfare, construction, and treaties. Their dedication to observing and predicting planetary movements showcased a blend of careful observations, mathematical innovation, and a desire to understand the forces that govern their world. What's truly inspiring is how they achieved all this without modern tools. They relied on persistent observation, recording data on clay tablets, and passing knowledge through generations. Their work laid the groundwork for future astronomers and mathematicians. The Babylonians' advancement in planetary observations and predictions highlight human curiosity at its finest. They didn't accept the movements in the sky as mere mysteries. They sought to understand and predict them. This quest for knowledge is a thread that connects us to them across the millennia. Their legacy reminds us that the desire to explore and make sense of the universe is a fundamental part of who we are. The Babylonians looked up at the same night sky that we see today, and through their ingenuity brought the heavens a little closer to Earth. Now let's explore one of the most impressive aspects of Babylonian astronomy, their use of mathematics to understand the heavens. It's truly remarkable how these ancient astronomers, without the tools we have today, developed complex techniques to calculate the movements of celestial bodies. Their work laid the groundwork for calendars we use even now. Imagine being a Babylonian scholar, sitting under the vast night sky filled with stars. You're determined to make sense of the patterns you see. Over time, you start noticing that celestial events repeat in cycles. The Babylonians were brilliant at spotting these patterns and turning them into mathematical formulas. One of their key achievements was creating methods to predict the positions of the moon and planets. They observed that the moon's motion wasn't constant. It sped up and slowed down at different points in its orbit. To model this, they used what's now called zigzag functions. Think of it like drawing a line that goes up and down in a zigzag pattern, which helped them account for the changes in speed. For the planets, they developed arithmetic sequences to predict where a planet would be in the sky at a given time. They used steps and intervals, adding or subtracting values based on their observations. This method allowed them to create tables that could forecast planetary positions years into the future. One of the most fascinating things they did was calculate the Saros cycle. This is a period of about 18 years, 11 days and 8 hours, after which lunar and solar eclipses repeat. By understanding this cycle, the Babylonians could predict eclipses with surprising accuracy. Imagine the awe and respect they must have commanded by foretelling such dramatic celestial events. But how did they use all this mathematical knowledge in everyday life? It all came down to their calendars. The Babylonians were deeply connected to the rhythms of nature, and having an accurate calendar was essential for agriculture, religious festivals, festivals and daily life. They combined their mathematical techniques with astronomical observations to develop both lunar and solar calendars. In the lunar calendar, the Babylonians noticed that the moon went through its phases, from new moon to full moon and back, in about 29.5 days. To keep track of this, they created months that were either 29 or 30 days long, aligning with the lunar cycle. A typical year would have 12 lunar months, totaling about 354 days. However, since this didn't match the solar year exactly, they added an extra month every few years, a process called intercalation, to keep their calendars in sync with the seasons. In solar calendar, they knew that the solar year, the time it takes for the Earth to orbit around the Sun, is about 365.25 days. Using their mathematical calculations, they accounted for this extra quarter of a day by adding an extra day every 4 years, much like we do with leap years. This helped them predict the changing of seasons accurately, which was crucial for farming activities like planting and harvesting. By combining the lunar and solar observations, they created a lunisolar calendar, balancing both cycles. This was no small feat. Their calendars were so precise that they could predict not just the seasons, but also the exact dates of important festivals and events. The Babylonians didn't have calculators or computers, yet they managed to perform complex mathematical operations using simple tools like clay tablets and styluses. They wrote down numbers using sexagesimal system, which is why we have 60 minutes in an hour and 360 degrees in a circle today, a lasting legacy of their mathematical brilliance. Their work wasn't just theoretical, it had practical applications that impacted their society every day. Farmers depended on calendars to know when to sow and reap. Priests used them to schedule religious ceremonies at precise times. Kings and rulers planned events and made decisions based on celestial predictions. Picture a Babylonian astronomer sharing his predictions with townspeople. In 3 months' time, there will be a lunar eclipse. When that day arrives and the moon darkens just as he said it would, imagine the sense of wonder and respect it inspired. Their ability to harness mathematics to decode the sky speaks volumes about human ingenuity. They turned observations into numbers, numbers into predictions, and predictions into a system that guided their entire civilization. The Babylonians' mathematical astronomy was a monumental achievement. They laid the foundations for the calendars we still use, and their methods influenced future generations of astronomers and mathematicians. It's a testament to their curiosity and dedication, and even thousands of years later, we are still captivated by their accomplishments. The brilliance of Babylonian astronomy didn't just stay within their own land. It spread far and wide, influencing civilizations that came after them, especially the Greeks and the Islamic world. The Greeks were fascinated by the sky just like the Babylonians, and they benefited immensely from Babylonian knowledge. The Greeks adopted the Babylonian zodiac system, dividing the sky into 12 sections, each with its own constellation. This became a cornerstone of Greek astronomy and astrology. Babylonian mathematical methods, especially their way of calculating planetary movements, influenced Greek astronomers. The Babylonians used a sexagesimal number system, which the Greeks found incredibly useful for astronomical calculations. That's why we still have 360 degrees in a circle today. Greek scholars like Hipparchus and Ptolemy build upon Babylonian observations. Hipparchus is known to have used Babylonian star catalogs to create his own, improving the accuracy of star positions. Ptolemy's famous work, the Almagest, drew heavily from the Babylonian data and methods. By integrating Babylonian insights into their own studies, the Greeks helped preserve and expand this knowledge, ensuring it wasn't lost over time. Centuries later, during the Islamic Golden Age, scholars in the Middle East became the new torchbearers of astronomical knowledge, and they too were greatly influenced by the Babylonians. In places like Baghdad's House of Wisdom, scholars gathered texts from all over, translating them into Arabic. Many Babylonian astronomical texts were among these works, preserved and studied with great enthusiasm. Islamic astronomers like Al-Khwarizmi and Al-Battani build upon Babylonian Greek foundations. Al-Khwarizmi's name gives us the word algorithm, and he was instrumental in developing algebra. Al-Battani refined the calculations of the solar year and improved the accuracy of astronomical tables. Inspired by earlier works, Islamic scholars established observatories to observe the sky more precisely. They compiled comprehensive star catalogs, echoing the Babylonian tradition of meticulous observation. The Islamic world became a crucial link in preserving and enhancing astronomical knowledge, which later found its way to Europe, spurring developments during the Renaissance. The survival level of Babylonian astronomical knowledge is nothing short of a miracle. The Babylonians recorded their observations on clay tablets using cuneiform script. These durable tablets survived millennia buried in desert sands. In the 19th and 20th century, archaeologists unearthed these tablets. Scholars worked tirelessly to decipher them, revealing a treasure trove of ancient knowledge. Through translations into Greek, Arabic, and eventually Latin, Babylonian astronomical texts reached a wider audience. This allowed their methods and discoveries to influence astronomers across different cultures and eras. The ripple effect of Babylonian astronomy are still felt today. Our 60-minute hours and 60-second minutes are based on the Babylonian-based 60 system. The division of circles into 360 degrees also comes from the Babylonian mathematics, aiding navigation, engineering, and astronomy. Many concepts in astrology trace back to Babylonian practices, showcasing their lasting cultural impact. The journey of Babylonian astronomical knowledge highlights something beautiful about human history: the sharing and building upon each other's discoveries. Each civilization didn't start from scratch, they learned from who came before them. The Babylonians provided a foundation for the Greeks, who passed the torch to Islamic scholars, who then influenced Renaissance Europe. This chain of knowledge reflects our shared curiosity about the universe. Despite differences in language, culture, and geography, the desire to understand the stars unites us. The Babylonians were pioneers, but their true legacy lies in how their insights sparked further discoveries around the world. Think about it, without their initial observations and mathematical techniques, our understanding of the cosmos might be very different today. They didn't just keep their knowledge to themselves. It traveled across borders and through time, influencing countless minds. Their story reminds us that knowledge is a living thing, nurtured by many hands and minds over generations. It's a testament to the power of human connection and the wonders we can achieve when we learn from one another. So, next time you look up at the night sky, remember the ancient Babylonian stargazers. Their eyes were among the first to systematically map the heavens, and their legacy continues to shine in every star we see. The ancient city of Athens, the heart of Greek culture and learning. The streets are filled with scholars, philosophers, and scientists, all eager to unlock the mysteries of the universe. The Greeks had a profound fascination with the cosmos, and astronomy was a crucial part of their quest for knowledge. Astronomy wasn't just a pastime for the Greeks, it was a window into the divine. They believed the heavens were the realm of the gods, and by studying the stars, they could understand the will of these powerful beings. Temples and observatories dotted the landscape, where dedicated astronomers watched the night sky, searching for patterns and meanings. The Greeks didn't start their astronomical journey from scratch. They built upon the rich knowledge passed down from earlier civilizations like the Babylonians. The Babylonians were meticulous record keepers, and their star catalogues and mathematical techniques provided a solid foundation for Greek astronomers. The Greeks admired the Babylonians' systematic approach to astronomy and sought to enhance it with their own observations and theories. One of the most revolutionary figures in Greek astronomy was Aristarchus of Samos. Imagine being Aristarchus in the 3rd century BCE, looking up at the night sky and daring to challenge the widely accepted geocentric model, which placed the Earth at the center of the universe. Aristarchus proposed a bold idea: the Sun, not the Earth, was the center of the universe, and the Earth orbited around it. This heliocentric model was revolutionary and ahead of its time. While it didn't gain immediate acceptance, it laid the groundwork for future astronomers like Copernicus to revisit and refine the concept. Another towering figure in Greek astronomy was Eratosthenes. As the chief librarian of Alexandria, Eratosthenes had access to wealth of knowledge. In the 3rd century BCE, he embarked on a scientific quest to measure the Earth's circumference. Using the angles of shadows cast by the sun in two different locations, Syene and Alexandria, and knowing the distance between them, Eratosthenes employed simple geometry to make his calculations. His estimate was remarkably close to the actual circumference of the Earth, showcasing his brilliance and the power of observation combined with mathematics. But Aristarchus and Eratosthenes weren't the only Greek astronomers who made significant contributions. Hipparchus, often hailed as the father of astronomy, created one of the earliest comprehensive star catalogues and discovered the precession of the equinoxes, a slow wobble in the Earth's axis. Ptolemy, another influential figure, compiled his astronomical knowledge in the Almagest, which became a cornerstone for future generations of astronomers. His geocentric model, placing the Earth at the center of the universe, dominated astronomical thought for centuries. Greek astronomers didn't just observe the stars. They sought to understand the underlying principles governing celestial movements. They developed sophisticated mathematical models to predict the positions of planets and timing of eclipses. Their work was a blend of observation, theory, and mathematics, reflecting their holistic approach to science. The contribution of Greek astronomers had a lasting impact on the world. Their work was preserved and expanded upon during the Islamic Golden Age as scholars translated Greek texts into Arabic and built upon their findings. This knowledge eventually reached Europe, sparking the Renaissance and leading to groundbreaking discoveries by figures like Copernicus, Galileo, and Kepler. Samos, a small island in the Aegean Sea, around the 3rd century BCE. Here lived Aristarchus of Samos, a brilliant mind with a curiosity about the cosmos that knew no bounds. Aristarchus was a Greek mathematician and astronomer who would go on to propose one of the most revolutionary ideas in the history of astronomy. Growing up in Samos, Aristarchus was likely influenced by the rich intellectual environment of the ancient Greece. This era was a time of philosophical exploration and scientific inquiry, with scholars seeking to understand the universe and humanity's place within it. Aristarchus studied under Strato of Lampsacus, a renowned philosopher which undoubtedly nurtured his love for learning and critical thinking. Aristarchus' most famous contribution to astronomy was his proposal of the heliocentric model, the idea that the Sun, not the Earth, was at the center of the universe. According to this model, the Earth and other planets orbited the Sun. Today, this might seem like common knowledge, but in Aristarchus' time, it was a radical departure from the prevailing view. Most people at the time adhered to the geocentric model, which placed the Earth at the center of the universe. This idea was deeply rooted in both observation and philosophy. Observationally, the Sun, Moon, and the stars seemed to move around the Earth, making it appear as though the Earth was stationary at the center. Philosophically, many believed that humans were the focal point of creation, and thus the Earth must be the center of everything. Aristarchus' heliocentric model was a bold challenge to this worldview. He reasoned that the apparent motion of the Sun around the Earth could be better explained by Earth's rotation on its axis and its orbit around the Sun. He also proposed that the stars were distant suns, suggesting the universe was much larger than previously thought. Despite the brilliance of his ideas, Aristarchus' heliocentric model didn't gain widespread acceptance in his own time. It was too radical, too different from the entrenched geocentric beliefs. People were not ready to shift their perspective so dramatically. The idea of moving Earth was hard to grasp, and there was no immediate observational evidence strong enough to sway the consensus. However, Aristarchus' work was not lost to history. It laid the groundwork for future astronomers who would revisit and expand upon his ideas. Copernicus, for instance, cited Aristarchus as an inspiration when he proposed his own heliocentric theory in the 16th century. Copernicus' work eventually led to a paradigm shift in astronomy, known as the Copernican Revolution, transforming our understanding of the cosmos. Aristarchus' influence extended beyond just the concept of heliocentrism. His methods of reasoning and his willingness to challenge established beliefs inspired other great thinkers. Johannes Kepler and Galileo Galilei built on heliocentric model, providing the necessary observations and mathematical support that Aristarchus lacked. Kepler's laws of planetary motion and Galileo's telescopic observations of celestial bodies provided compelling evidence that the Earth indeed orbits the Sun. In addition to his work on heliocentrism, Aristarchus also made significant contributions to understanding the sizes and distances of the Sun and Moon relative to the Earth. He used geometric methods to estimate the relative sizes of these celestial bodies and their distances from the Earth. Although his estimates weren't accurate by today's standards, they were a remarkable attempt at quantifying the cosmos with the tools available at the time. It is the 3rd century BCE, and the Library of Alexandria stands as a beacon of knowledge, attracting scholars from all over the world. Among them is Eratosthenes, a man whose curiosity and intellect would lead him to make one of the most remarkable calculations in history. Born around 276 BCE in Cyrene, modern-day Libya, Eratosthenes was a polymath, skilled in various fields such as mathematics, astronomy, geography, and poetry. His thirst for knowledge led him to Athens, where he studied philosophy and science, and later to Alexandria, where he was appointed the chief librarian of the Great Library. This prestigious position gave Eratosthenes access to vast array of texts and resources, fueling his passion for learning and discovery. One of Eratosthenes' most famous achievements was his calculation of Earth's circumference. The story of how he accomplished this is both simple and ingenious. Eratosthenes has heard that in the city of Syene, modern-day Aswan in Egypt, located directly south of Alexandria, the sun was directly overhead at noon on the summer solstice. This meant that vertical objects cast no shadows, and the reflection of the sun could be seen in the water of the deep wells. In Alexandria, however, the vertical objects did cast shadows at the same time, indicating that the sun was at an angle. Eratosthenes realized that if he could measure this angle, he could use it to calculate the Earth's circumference, and here is how he did it. On the summer solstice, Eratosthenes measured the angle of the shadow cast by a vertical stick in Alexandria. He found the angle to be approximately 7.2 degrees, which is about 1/50th of a full circle. Eratosthenes knew the approximate distance between Syene and Alexandria, which was about 800 kilometers. This distance had been measured by surveyors using the travel time of camel caravans. Using the angle and the distance, Eratosthenes set up a simple proportion. If 7.2 degrees corresponds to 800 kilometers, then 360 degrees, the full circumference of the Earth, would correspond to 40,000 kilometers. Eratosthenes' calculation was remarkably close to actual circumference of the Earth, which is about 40,075 kilometers. Considering the limited tools and knowledge of his time, this was an extraordinary achievement, showcasing his brilliance and the power of observation combined with geometry. But Eratosthenes' contribution didn't stop there. He made significant advancements in geography by devising a system of latitude and longitude to map the known world, providing a framework that would be used for centuries. His work in geography earned him the title Father of Geography. Eratosthenes also invented the concept of leap year. He noticed that the solar year didn't consist exactly of 365 days, but was approximately 365.25 days. To account for the extra quarter day, he proposed adding an extra day to calendar every 4 years. This simple yet effective adjustment helped to keep the calendar in sync with the seasons. Beyond these practical achievements, Eratosthenes was a prolific writer and thinker. He wrote books on a wide range of subjects, from philosophy to literary criticism. Unfortunately, most of his works have been lost to history, but references to them by later scholars attest to his intellectual versatility and influence. Eratosthenes' approach to learning and discovery was holistic, integrating observations, mathematics, and logic to answer some of the most profound questions of his time. His calculation on the Earth's circumference wasn't just a mathematical feat, it was a testament to the idea that through careful observation and reasoning, humans could understand the natural world with astonishing accuracy. One of the standout figures in Greek astronomy is Hipparchus of Nicaea. Born around 190 BCE, Hipparchus is often referred to as the father of astronomy. His meticulous observations and mathematical prowess laid the groundwork for many future discoveries. Hipparchus created one of the earliest comprehensive star catalogues, which listed the positions of over 850 stars. He meticulously measured the positions and brightness of these stars, providing a reference point for future astronomers. He made a groundbreaking discovery known as the precession of the equinoxes. This is the slow wobble of the Earth's axis, which causes the positions of the equinoxes to shift over time. By comparing his observations with those of earlier astronomers, Hipparchus realized that the equinoxes had moved, and he accurately estimated the rate of this precession. This discovery was monumental, showing the dynamic nature of the heavens. Hipparchus's work built upon the foundations laid by earlier astronomers like Aristarchus. While Aristarchus proposed the heliocentric model, Hipparchus focused on refining the geocentric model, where the Earth remained at the center. He developed sophisticated mathematical models to predict the movements of the sun, moon, and the planets, making significant advancements in accuracy of these predictions. Let's move forward a few centuries to meet Claudius Ptolemy, another towering figure in Greek astronomy. Ptolemy lived in Alexandria during the 2nd century CE and is best known for his work, the Almagest. This comprehensive catalogue compiled much of astronomical knowledge of the time and became the authoritative reference for astronomers for over 1,000 years. Ptolemy's contributions were immense. He expanded upon Hipparchus's work, refining the geocentric model with a series of complex mathematical systems. Ptolemy introduced the concept of epicycles, small circular orbits that the planets followed while also moving along larger circular paths around the Earth. This model, known as the Ptolemaic system, explained the retrograde motion of planets, where they appeared to move backward in the sky. While the Ptolemaic system was later replaced by the heliocentric model proposed by Copernicus, it was an incredibly effective tool for predicting celestial movement. Ptolemy's work demonstrated the Greeks' ability to create intricate models to explain their observations, even if the underlying assumptions, like Earth being at the center, were incorrect. Ptolemy also contributed to other fields, such as geography. His work Geographia was a comprehensive compilation of world's knowledge, including maps and coordinates, further highlighting his intellectual versatility. These great Greek astronomers build upon the observation and theories of their predecessors, enhancing our understanding of the universe. While Aristarchus' heliocentric model was revolutionary, it wasn't widely accepted in their time. Hipparchus and Ptolemy instead focused on refining the geocentric model, which aligned the prevailing views of the heavens. Let's meet two more remarkable thinkers, Thales of Miletus and Anaximander. These early philosophers didn't just ponder the big questions, they tried to answer them with observations and reasoning, laying the groundwork for science and astronomy. Thales of Miletus is often hailed as the first Greek astronomer. Born around 624 BCE in a bustling city of Miletus, Thales had a curious mind that sought to understand the world in new ways. He is famously known for predicting a solar eclipse. Imagine the awe and wonder he inspired when, without modern technology, he forecasted that the sun would be obscured and casting a shadow over the land. This event was a turning point, showing that the movements of the celestial bodies could be understood and predicted. Thales also had some intriguing ideas about the Earth. He believed that the Earth floated on water like a log in the pond. While this might sound strange for us today, it was a significant step towards thinking about the Earth's place in the universe. Thales' ideas was based on observation that water was essential for life and seemed to be everywhere, from seas to rivers to rain. By imagining the Earth floating on water, he was trying to explain natural phenomena in a tangible way, moving away from mythological explanations. Now, let's talk about Anaximander, a student of Thales who took his teacher's ideas even further. Anaximander was born around 610 BCE also in Miletus, and he was a true pioneer in his own right. He proposed that the Earth was not floating on water, but was a cylinder suspended in space. This was a radical idea because it suggested that Earth wasn't resting on anything, a concept that took a big leap away from the common beliefs of the time. Anaximander didn't stop there. He introduced the idea of the Milky Way as a collection of stars. Imagine looking up at the night sky and seeing that faint, cloudy band of light stretching across the heavens. Anaximander suggested that this glow came from countless stars clustered together, their combined light forming the Milky Way. This insight showed his deep observational skills and his ability to think beyond the visible to understand the cosmos. Both Thales and Anaximander were not just theorists, they were practical observers. They used what they saw to formulate ideas about the natural world. Thales' prediction on the solar eclipse, for example, wasn't just a lucky guess. It was based on his understanding of the cycles of the sun and the moon. Anaximanders' concept of the Earth as a cylinder and his thoughts on the Milky Way were rooted in his careful observations of the sky. Their contributions laid the foundations for future astronomers and philosophers. They were among the first to seek natural explanations for the world around them, moving away from the mythological and supernatural interpretations. This approach opened the door for a more systematic study of the universe, which later Greek thinkers like Pythagoras, Plato, and Aristotle would continue to develop. In essence, Thales and Anaximander were early explorers of the cosmos, using their keen observations and innovative thinking to ask big questions and seek answers in the natural world. Their legacy lives on in the spirit of curiosity and inquiry that drives science and astronomy today. These early stargazers remind us that the journey to understand the universe began with simple yet profound questions about the world around us. The work of Greek astronomers didn't just vanish with time. Instead, it was carefully preserved, studied, and expanded upon by later civilizations. One of the most significant periods for the preservation and transmission of Greek astronomical ideas was the Islamic Golden Age, spanning roughly from the 8th to 14th century. During this time, the Islamic world became the torchbearer for scientific knowledge. In Baghdad's House of Wisdom, scholars translated Greek texts into Arabic, making them accessible to a broader audience. The works of Ptolemy, for example, were translated and studied in detail. Islamic astronomers like Al-Khwarizmi and Al-Battani not only preserved these texts but also build upon them, refining and expanding the knowledge they contained. Al-Battani, often called the Ptolemy of Islam, made significant improvements to Ptolemaic astronomy, including more accurate measurements of the length of the solar year and movement of the planets. The meticulous star catalogues of Hipparchus and the mathematical models of Ptolemy served as essential references for Islamic astronomers, who in turn made their contributions to the field. This period of scientific flourishing ensured that Greek astronomical knowledge was not lost but rather enriched and passed on to the future generations. As the knowledge of Islamic world began to spread into Europe, particularly during the Renaissance, these ancient Greek ideas found new life. European scholars eagerly translated Arabic texts into Latin, rediscovering the astronomical works of the Greeks through the lens of the Islamic scholarship. This intellectual revival set the stage for one of the most transformative periods in history of science. Enter Nicolaus Copernicus, a Renaissance mathematician and astronomer who would change the course of astronomy forever. Copernicus was deeply influenced by the works of ancient Greeks and Islamic astronomers. He studied Ptolemy's geocentric model but was also aware of Aristarchus's heliocentric hypothesis. Copernicus dared to revisit and expand upon Aristarchus's idea that the Sun, not the Earth, was at the center of the universe, and Copernicus' heliocentric model had a profound impact on the scientific revolution. The Greeks were visionaries, transforming the way humanity perceived the cosmos through their meticulous observations, bold hypotheses, and ingenious mathematical models. The work of Greek astronomers like Aristarchus, Eratosthenes, Hipparchus, and Ptolemy laid the foundation that has endured through the ages. Aristarchus's daring heliocentric model challenged the geocentric worldview, sowing the seeds for future revolutions in astronomical thought. Eratosthenes' accurate calculations of the Earth's circumference demonstrated the power of observation and geometry, providing a model of scientific inquiry that continues to inspire. Hipparchus' star catalogue and discovery of the precession of the equinoxes showcased the Greeks' commitment to precision and their ability to detect subtle changes in the heavens. Ptolemy's comprehensive catalogue, the Almagest, compiled and refined centuries of astronomical knowledge, becoming a cornerstone for scholars across cultures and eras. Greek astronomy didn't just stay confined to the Mediterranean. It traveled far and wide, influencing subsequent civilizations and shaping the course of scientific progress.
From the Great Wall stretching across the northern plains to the terraced fields of the south, China was a civilization deeply connected to the rhythms of nature and the cosmos. The Chinese have a long history of observing the heavens, believing that the movements of celestial bodies held the secrets to understanding the natural world and guiding their society. The rich cultural heritage of ancient China is intertwined with their advancements in astronomy. For the Chinese, the sky was a canvas painted with the will of the gods and ancestors. They saw the cosmos as a harmonious reflection of the earthly realm, and by studying the stars, they sought to align themselves with the divine order. Astronomy in ancient China wasn't just an academic pursuit, it was a vital part of governance and daily life. The emperor, often referred to as the son of heaven, was seen as the link between the celestial and earthly realms. Maintaining harmony between these two worlds was essential for ensuring peace and prosperity. To do this, the Chinese developed an intricate system of celestial observation to predict events and guide decision-making. Celestial observations played a crucial role in Chinese history, helping to shape the agricultural calendar, which in turn influenced crop planting and harvesting. By accurately predicting the seasons, ancient Chinese astronomers ensured that their society could thrive and avoid devastating effects of poor planning. The development of sophisticated calendar systems such as the lunisolar calendar was one of their remarkable achievements. This calendar combined lunar months with solar years, ensuring that festivals and agricultural activities remained synchronized with the natural world. In addition to its practical applications, astronomy had a deep spiritual and symbolic significance in Chinese culture. The Chinese divided the sky into specific regions associated with mythological creatures and deities. For example, the sky was divided into 4 quadrants, each represented by a celestial animal: the azure dragon of the east, the black tortoise of the north, the white tiger of the west, and the vermilion bird of the south. This division not only only helped in mapping the heavens, but also connected astronomical observations to cultural and religious beliefs. One of the earliest and most significant achievements in Chinese astronomy was the creation of detailed star maps. These maps, also known as star charts, recorded the positions of stars and constellations, allowing astronomers to track celestial movements and predict future events. The Dunhuang star chart, dating back to Tang Dynasty, is one of the oldest surviving examples, showcasing the precision and dedication of Chinese astronomers. The significance of celestial observations in Chinese history cannot be overstated. These observations were meticulously recorded and used to interpret events on Earth. For example, the appearance of comets and the occurrence of supernovae were seen as omens, signaling significant changes or events. One famous example is the recording of the supernova SN 1054, which created the Crab Nebula. Ancient Chinese astronomers documented this event in detail, providing valuable historical data that continues to be studied by modern astronomers. Chinese astronomers also played a critical role in timekeeping. They developed various devices such as water clocks and the gnomon, a type of sundial to measure time accurately based on the sun's position. These advancements in timekeeping were essential for maintaining the calendar and scheduling important activities. As we set the stage for exploring the astronomical achievements of ancient China, it's clear that their contributions were vast and varied. From the development of star maps to the recording of celestial events and the creation of sophisticated calendar systems, Chinese astronomers demonstrated a deep connection to the heavens. Their work laid the foundation for future discoveries and highlighted the importance of aligning human activities with the natural and divine order. Continuing our exploration into the wonders of ancient Chinese astronomy, let's delve into one of their most remarkable achievements, the creation of the first star map. These maps, also known as star charts, were detailed records of positions of stars and constellations, and they played a crucial role in the development of astronomy. The ancient Chinese were meticulous observers of the night sky, and they realized early on that mapping the stars could help them better understand the cosmos. These star maps weren't just artistic representations. They were practical tools that allowed astronomers to track celestial movements and predict future events. Imagine the dedication it took to stand under the vast expanse of the night sky, night after night, charting the positions of countless stars. One of the earliest and most significant examples of these star maps is the Dunhuang star chart. This ancient manuscript, dating back to the Tang Dynasty, is a true testament to the precision and dedication of Chinese astronomers. The Dunhuang star chart is one of the oldest surviving star maps in the world, and it provides a fascinating glimpse into the astronomical knowledge of ancient China. The Dunhuang star chart was discovered in the Mogao Caves, also known as the Caves of Thousand Buddhas, located in the Dunhuang region of northwestern China. These caves were a major center of Buddhist worship and learning, and the star chart was found among a treasure trove of manuscripts that had been sealed in a hidden library for centuries. The chart itself is a detailed and accurate depiction of the night sky, featuring over 1,300 stars arranged into more than 250 constellations. The creation of these star maps had immense significance. For ancient Chinese astronomers, accurately recording the positions of stars and constellations was essential for a variety of reasons. Firstly, it allowed them to develop more precise calendar systems. By tracking the movement of stars and constellations, they could predict the change in seasons, which was crucial for agricultural planning. Knowing when to plant and harvest crops could mean the difference between a bountiful harvest and a devastating famine. Secondly, star maps were used for navigation. By knowing the positions of key constellations, travelers and sailors could find their way across vast distances, whether on land or at sea. The stars provided a reliable guide, helping to ensure safe journeys and the successful completion of trade missions. Thirdly, star maps held significant cultural and spiritual importance. The ancient Chinese believed that the heavens reflected the earthly realm, and that celestial events could influence human affairs. By studying the stars, they sought to understand the will of the gods and ancestors, and to align their actions with the divine order. This connection between the cosmos and daily life is beautifully illustrated in the intricate star maps created by Chinese astronomers. In addition to the Dunhuang star chart, other notable examples include the star maps from the Tang and Song dynasties. These maps continued to build on the knowledge of earlier astronomers, refining the accuracy and detail of celestial charts. The work of these astronomers showcased their ability to observe the night sky with remarkable precision and to document their findings in ways that would endure for centuries. The development of star maps by ancient Chinese astronomers was a monumental achievement that not only advanced the field of astronomy, but also had profound implications for society. These maps were more than just scientific tools. They were a means of connecting with the divine, ensuring the well-being of the community and navigating the world. The dedication and skill of these early stargazers laid the foundation for future discoveries, inspiring astronomers across cultures and eras. Records of supernovae and comets reveal the incredible dedication and observational skills of Chinese astronomers. These celestial events weren't just spectacular sights in the night sky, but were carefully documented to provide valuable insights into the workings of the universe. Chinese astronomers were among the first to systematically record supernovae and comets, recognizing their importance in understanding celestial phenomena. Imagine standing under the vast expanse of the night sky, observing the sudden appearance of a new bright star or the long glowing tail of a comet. These events were seen as omens or messages from the heavens, and the Chinese took great care to document them in detail. One of the most famous recorded supernovae is SN 1054, observed in 1054. This supernova was so bright that it was visible in the daylight for several weeks and remained visible in the night sky for nearly 2 years. Ancient Chinese astronomers meticulously recorded this event, noting the position in the night sky, its brightness, and its duration. This supernova explosion eventually led to the formation of Crab Nebula, a beautiful and intricate remnant still studied by astronomers today. The records of SN 1054 provide a wealth of historical data that modern astronomers use to understand the life cycle of stars. By comparing ancient observations with current data, scientists can track the evolution of supernova remnants over centuries. The detailed documentation of SN 1054 by Chinese astronomers is a testament to their commitment to capturing these celestial events with precision. But the Chinese didn't just record supernovae. They also kept extensive records of comets. Comets were considered significant celestial visitors, often interpreted as harbingers of change or important events. The ancient Chinese developed a system to classify comets based on their appearance, duration, and movement. They noted details such as the length and direction of the comet's tail, the color and brightness of the comet, and any changes in its behavior over time. These comet records were systematic and thorough, providing a comprehensive view of each observed comet's characteristics. For example, the Chinese astronomers recorded the appearance of Halley's Comet in 240 BCE, one of the earliest known sightings of this famous comet. They meticulously noted its path across the sky and its visible features, creating a valuable historical record that aligns with modern observations of Halley's Comet. The precise recording of supernovae and comets by ancient Chinese astronomers wasn't just about capturing the beauty of the night sky. These records served a practical purpose, such as predicting the timing of agricultural activities, aligning religious ceremonies, and advising rulers on political decisions. By understanding the movements and appearances of these celestial phenomena, the Chinese sought to harmonize their lives with the rhythms of the cosmos. Their detailed and systematic observations provide a rich source of historical data that continues to inform and enhance modern astronomical research. The records of SN 1054, for example, offer a unique opportunity to study the long-term evolution of a supernova remnant, while the extensive comet records help scientists understand the behavior and characteristics of these icy wanderers. As we continue our journey through ancient Chinese astronomy, let's take a closer look at their remarkable achievements in developing sophisticated calendar systems and timekeeping devices. These advancements were essential for synchronizing agricultural activities, festivals, and governance, ensuring that society could function smoothly with the rhythms of the cosmos. The ancient Chinese placed great importance on aligning their daily lives with the movements of the heavens. They developed calendars that combined lunar and solar cycles, known as the lunisolar calendars, to accurately track the passage of time. This careful synchronization was crucial for planning agricultural activities, determining the dates of important festivals, and guiding governance decisions. The lunisolar calendar was a brilliant innovation that balanced the cycles of the moon and the sun. The lunar cycle, with its phases of new moon to full moon, takes approximately 29.5 days. A typical lunar year consisting of 12 lunar months added up to about 354 days, which is shorter than the solar year of approximately 365.25 days. To reconcile this difference, Chinese astronomers introduced an extra month, called an intercalary month, every few years. This process of intercalation ensured that the calendar stayed in sync with the solar year and the changing seasons. The lunisolar calendar was not only a practical tool for farming, but also played a significant role in Chinese culture and religion. Festivals and rituals were often tied to specific lunar phases or solar events, and an accurate calendar was essential for maintaining these traditions. For example, the famous Chinese New Year, which marks the beginning of the lunar year, is celebrated based on the lunar calendar. Other festivals, such as the Mid-Autumn Festival, are also tied to lunar phases, highlighting the deep connection between celestial observations and cultural practices. In addition to developing sophisticated calendar systems, ancient Chinese astronomers invented various timekeeping devices to measure time accurately. One of the earliest and most significant inventions was the gnomon, a simple yet effective sundial. The gnomon consisted of a vertical stick or a pillar that cast a shadow on a marked surface. By observing the position and length of the shadow throughout the day, astronomers could determine the time and track the movement of the sun across the sky. The gnomon was a vital tool for calibrating other timekeeping devices and for conducting astronomical observations. It helped astronomers measure the length of the solar day, determine the solstices and equinoxes, and establish the noon meridian. The gnomon's simplicity and accuracy made it an essential instrument in the early development of Chinese astronomy. Another significant timekeeping invention was the water clock. The ancient Chinese developed various designs of a water clock to measure the passage of time based on the steady flow of water. One common type was the clepsydra, which consisted of a vessel with a small hole at the bottom, allowing water to drip at a constant rate into another container. By measuring the amount of water collected over a specific period, the time could be determined. Water clocks were used for a variety of purposes, including regulating daily activities, scheduling official duties, and conducting astronomical observations. The accuracy of water clocks improved over time, with more complex designs incorporating gears and other mechanisms to enhance precision. The water clock's ability to measure time continuously, even at night or on cloudy days when the sun was not visible, made it an invaluable tool for ancient Chinese astronomers and scholars. The development of sophisticated calendar systems and timekeeping devices by ancient Chinese astronomers showcased their ingenuity and deep connection to the cosmos. These advancements were not just about measuring time, they were about harmonizing human activities with the natural world and the divine order. By accurately tracking the movement of the heavens, the Chinese ensured that their society could thrive and prosper in harmony with the celestial cycles. As we delve deeper into the achievements of ancient Chinese astronomy, it's essential to highlight the incredible contributions of notable astronomers like Zhang Heng and Zhuo Shoujing. These brilliant minds not only advanced the field of astronomy, but also left a lasting legacy with their innovative inventions and reforms. Zhang Heng, born in 78 CE, was a true polymath. His interests span across astronomy, mathematics, engineering, and literature. One of his most famous inventions was the seismoscope, an early earthquake detector that demonstrated his deep understanding of natural phenomena. The seismoscope, invented around 132 CE, was a remarkable device shaped like a large bronze urn. It had 8 dragon heads positioned around the rim, each holding a bronze ball in its mouth. Below each dragon head was a toad figure with an open mouth. When an earthquake occurred, the internal mechanism of the seismoscope would detect the seismic waves and cause one of the dragon heads to release a ball into the corresponding toad's mouth. The direction of the released ball indicated the direction of the earthquake's epicenter. This ingenious invention provided early warnings of seismic activity and showcased Zhang Heng's ability to translate his observations into practical applications. But Zhang Heng's contributions didn't stop there. He also created a celestial globe, an intricate model of the night sky that helped astronomers visualize the positions and movements of celestial bodies. This globe was driven by a water-powered mechanism, allowing it to rotate and simulate the apparent motion of the stars and planets. The celestial globe was an essential tool for teaching and studying astronomy, demonstrating the harmonious order of the cosmos and interconnectedness of celestial phenomena. Moving forward to the 13th century, we meet another exceptional figure in Chinese astronomy, Zhuo Shoujing. Born in 1231 during the Yuan dynasty, Zhuo Shoujing was a renowned astronomer, engineer, and mathematician. His work significantly advanced the accuracy of astronomical observations and calendar systems. One of Zhuo Shoujing's most notable achievements was his reforms to the Chinese calendar. The existing calendar systems at the time were becoming increasingly inaccurate due to the accumulated errors over the centuries. Zhuo Shoujing was tasked with creating a new, more precise calendar. In 1280, he introduced the Shou-Shi Li calendar, which improved the calculation of the solar year and the lunar month. His reforms included more accurate measurements of Earth's orbit and the Moon's cycles, ensuring that the calendar remained in sync with natural world. The Shouxi Li calendar was highly regarded for its precision and was used for several centuries. Guo Shoujing also developed advanced astronomical instruments that furthered the study of the heavens. One of his most significant inventions was the simplified armillary sphere, a three-dimensional model representing the celestial sphere. This instrument allowed astronomers to measure the positions of stars and planets with greater accuracy. Guo Shoujing's simplified design made it easier to construct and use, contributing to more precise observations and calculations. Another Guo Shoujing's innovation was the gnomon, a device used to measure the angle of the sun's shadow and determine the time of the day. While the gnomon was not a new invention, Guo Shoujing refined its design and improved its accuracy. His version of the gnomon was used to conduct detailed solar observations, which were essential for calibrating other astronomical instruments and refining calendar calculations. The contributions of Zhang Heng and Guo Shoujing highlight the ingenuity and dedication of Chinese astronomers. Their inventions and reforms had a profound impact on the field of astronomy, demonstrating practical applications of celestial observations in everyday life. Zhang Heng's seismoscope and celestial globe showcased his ability to turn theoretical knowledge into functional tools, while Guo Shoujing's calendar reform and advanced instruments ensured the continued accuracy and reliability of astronomical data. As we reflect on the achievements of these key figures, we see a legacy of innovation and precision that continues to inspire astronomers today. The work of Zhang Heng and Guo Shoujing laid the foundation for future discoveries, contributing to our understanding of the cosmos and our ability to navigate the complexities of natural world. The meticulous observations, innovative instruments, and sophisticated calendar systems developed by Chinese astronomers didn't just remain within the borders of China. They traveled far and wide, influencing the course of astronomical progress across the world. One of the key periods when Chinese astronomical knowledge was shared and expanded upon was during the Ming Dynasty. During this time, China experienced a flourishing of culture, science, and exploration. It was also a period of increased interactions with the Western world, especially through the efforts of Jesuit missionaries. These missionaries brought with them not only their religious teachings, but also their knowledge of European science and astronomy. The collaboration between Chinese astronomers and Jesuit missionaries during the Ming Dynasty was a remarkable example of the exchange of ideas that enriched both Eastern and Western astronomical traditions. Jesuit missionaries such as Matteo Ricci arrived in China with a deep appreciation for Chinese culture and a desire to share their scientific knowledge. They brought with them advanced European astronomical instruments and introduced new methods of observation and calculation. In return, the Jesuit missionaries were eager to learn from Chinese astronomers who had centuries of accumulated knowledge and experience. This exchange of ideas led to fruitful collaboration that benefited both sides. Chinese astronomers gained access to new tools and techniques, while the Jesuits were able to incorporate Chinese observations and data into their own studies. One of the significant outcomes of this collaboration was the improvement of Chinese calendar systems. The existing Chinese calendar had accumulated errors over time, leading to discrepancies between the observed and predicted celestial events. The Jesuits, with their advanced knowledge of European astronomy, helped to correct these errors and refine the calendar. Their work, combined with the expertise of Chinese astronomers, resulted in more accurate and reliable calendars that better aligned with the natural cycles. Another notable achievement was the construction of advanced astronomical instruments that combined both Chinese and Western designs. The Jesuits introduced the telescope to China, which revolutionized the way celestial observations were conducted. Chinese astronomers quickly adopted this new technology, using it to enhance their observations of stars, planets, and other celestial phenomena. The collaboration also led to the creation of comprehensive astronomical texts that incorporated knowledge from both traditions. The Chongzhen Li Shu, an astronomical treatise compiled during the reign of the Chongzhen Emperor, is a prime example of this fusion of Eastern and Western astronomy. It included detailed observations, calculations, and descriptions of celestial events, reflecting the combined efforts of Chinese astronomers and Jesuit missionaries. The influence of Chinese astronomical achievements extended beyond the Ming Dynasty. The knowledge exchanged during this period continued to spread and inspire astronomers around the world. Chinese star maps, records of supernovae and comets, and sophisticated calendar systems were studied and admired by scholars in neighboring cultures and later civilizations. The detailed documentation of celestial events provided valuable historical data that informed and enriched the work of astronomers astronomers for generations to come. The exchange of ideas between Chinese astronomers and Jesuit missionaries highlights the importance of cross-cultural collaboration in advancing scientific knowledge. It demonstrates how the blending of different perspectives and techniques can lead to significant advancements and a deeper understanding of the cosmos. This spirit of collaboration and shared curiosity is a testament to the universal human quest to explore and comprehend the wonders of the universe. Throughout the ages, ancient Chinese astronomers made remarkable strides in understanding the cosmos. Their meticulous observations and innovative approaches significantly shaped astronomy. The legacy of ancient Chinese astronomy is a testament to their dedication, curiosity, and profound connection to the cosmos. Their contributions continue to inspire and inform our understanding of the universe today.
Imagine a world thousands of years ago, long before modern technology, where people relied on the stars to guide their way. This was ancient India, a land of incredible knowledge and wisdom. Our story begins here, with the brilliant minds who looked up to the night sky and sought to understand its secrets. These early astronomers weren't just dreamers, they were meticulous observers and gifted mathematicians who made groundbreaking discoveries. In ancient India, astronomy was more than just a science. It was woven into the very fabric of daily life. The night sky held a great significance in Hinduism and other Indian religions. Celestial bodies like the sun, moon, and the stars influenced everything from agriculture to religious rituals. People believed that the movements of these heavenly objects could impact their lives and decisions. One of the earliest periods where we find traces of this astronomical knowledge is the Vedic period. During this time, ancient Indian scriptures such as the Rig Veda and Atharva Veda were composed. These texts are filled with references to celestial bodies, showing how deeply astronomy was embedded in the spiritual and cultural life of the people. Hymns and chants often praised deities associated with the sun, moon, and the stars, highlighting their importance in the universe. Our journey through the history of Indian astronomy wouldn't be complete without mentioning Aryabhata. Born in 476 CE, Aryabhata was a true pioneer who calculated the length of the solar year with remarkable precision. He also proposed the revolutionary idea that the Earth rotates on its axis. His work, documented in his famous book Aryabhatiya, laid the foundation for many future discoveries in both astronomy and mathematics. Next, we meet Brahmagupta. Born in 598 CE, Brahmagupta made significant contributions to our understanding of gravity and planetary motion. His remarkable work on lunar and solar eclipses showcased his mathematical brilliance and deep understanding of the cosmos. Our story will also introduce you to other influential astronomers like Varahamihira, Bhaskara I and Bhaskara II, who made tremendous strides in trigonometry, calculus, and planetary motion. Their contributions left a lasting legacy that continues to inspire scientists today. Picture yourself in ancient India, thousands of years ago, where the night sky was a canvas of twinkling stars and planets. The people of this time were deeply connected to the cosmos, finding meaning and guidance in the patterns they observed. This is where our story begins, during the Vedic period, a time when astronomy was interwoven with spirituality and daily life. The Vedic period, which dates back to around 1500 BCE to 500 BCE, was an era of profound knowledge and wisdom. The ancient Indian scriptures from this time, such as the Rig Veda and the Atharva Veda, are treasure troves of astronomical references. These texts reveal that the early Indians were keen observers of the sky, recording the movements of celestial bodies with remarkable accuracy. The Rig Veda, one of the oldest known texts in human history, is filled with hymns that praise the gods associated with the sun, moon, and the stars. The sun, or Surya, was revered as the source of all life, its daily journey across the sky symbolizing the eternal cycle of birth, death, and rebirth. The moon, or Chandra, was also significant, influencing the rhythms of time and seasons. One of the most fascinating contributions of the Vedic period to astronomy is the concept of timekeeping. The ancient Indians developed a sophisticated calendar system based on the lunar and solar cycles. They divided the year into 12 months, each corresponding to a specific phase of the moon. This calendar not only helped them to keep track of agricultural activities, but also played a crucial role in religious rituals and festivals. The Atharva Veda, another important text from this period, contains numerous references to celestial events like eclipses and the movements of planets. The early Indians believed that these events were not mere coincidences but had deeper cosmic significance. They saw eclipses as powerful omens often associated with the actions of gods and demons. The priests and sages of this time would perform elaborate rituals to appease the gods and ensure the well-being of the community. The nakshatras, or lunar mansions, are another key element of Vedic astronomy. The sky was divided into 27 or 28 nakshatras, each representing a segment of the moon's monthly journey. The nakshatras were personified as deities and played a crucial role in astrological predictions. The position of the moon within these nakshatras at the time of one's birth was believed to influence their destiny and character. As our story unfolds, we see that the Vedic period laid the foundation for a rich tradition of astronomical knowledge in ancient India. The early Indians were not just passive observers of the night sky. They actively sought to understand the cosmos and its influence on their lives. 5th century CE. In a land brimming with intellectual curiosity is where Aryabhata's story begins. Aryabhata was born in 476 CE in a small village called Kusumapura, near present-day Patna in Bihar, India. Even as a young boy, Aryabhata exhibited a remarkable curiosity about the world around him. His keen mind and thirst for knowledge led him to study under the best scholars of his time. As he grew, Aryabhata's passion for mathematics and astronomy flourished. By the age of 23, he had written his magnum opus, the Aryabhatiya. This groundbreaking work, composed in Sanskrit, was a comprehensive treatise on mathematics and astronomy. It was divided into 4 sections: the Gitikapada, on time and its measurement, the Ganitapada, on mathematics, the Kalakriyapada, on astronomy, and the Golapada, on the sphere. The Aryabhatiya was a testament to Aryabhata's genius and laid the foundation for many future discoveries. One of Aryabhata's most significant contributions was his accurate calculation of the solar year. He determined that the length of the solar year was 365.358 days, which was very close to the modern value of 365.256 days. This precision was achieved through meticulous observation and mathematical prowess, demonstrating Aryabhata's exceptional understanding of celestial mechanics. But Aryabhata didn't stop there. He also proposed the revolutionary idea that the Earth rotates on its axis. In a time when most people believed that the Earth was stationary and the heavens revolved around it, Aryabhata's suggestion was groundbreaking. He explained that the apparent motion of the stars and the planets could be attributed to the Earth's rotation, a concept that was far ahead of its time. Aryabhata's contributions to mathematics were equally impressive. He introduced the concept of zero as a placeholder and used it in calculations, a practice that would later revolutionize mathematics. He also developed methods for solving complex algebraic equations and worked on the approximation of pi, estimating it to be approximately 3.1416, which is astonishingly close to the true value. In his Aryabhatiya, Aryabhata also tackled the problem of calculating the circumference of Earth. Using his knowledge of trigonometry, he estimated the Earth's circumference to be about 39,968 kilometers, which is very close to the actual value of 40,075 kilometers. This achievement demonstrated not only his mathematical brilliance, but also his ability to apply theoretical knowledge to practical problems. Another of Aryabhata's major works was the Arya Siddhanta, although much of it has been lost to history. What remains of this text reveals Aryabhata's deep understanding of planetary motion and eclipses. He accurately predicted solar and lunar eclipses and explained their causes, attributing them to the shadows cast by the Earth and the Moon. Aryabhata's legacy extends far beyond his own time. His works influenced generations of Indian and Islamic astronomers and mathematicians. His innovative ideas and precise calculations laid the groundwork for future discoveries and advancements in both fields. Now, let's delve into the remarkable life of Varahamihira, one of the most influential figures in ancient astronomy and astrology. Picture yourself in the early 6th century CE, in the vibrant atmosphere of Ujjain, a city renowned for its scholars and thinkers. This is where Varahamihira's story begins. Varahamihira was born in 505 CE, in a small village in what is now modern-day India. His early life was steeped in the rich traditions of Indian scholarship. From a young age, Varahamihira showed an extraordinary aptitude for learning, particularly in the fields of mathematics and astronomy. He was taught by his father, Adityadasa, a distinguished scholar in his own right, who recognized his son's prodigious talent and nurtured it with great care. Varahamihira's curiosity and brilliance led him to Ujjain, a city that was a hub of academic and scientific activity. It was here that he flourished, surrounded by the leading minds of his time. His intellectual pursuit culminated in the creation of his work, the Panchasiddhantika. This monumental work was a comprehensive compilation of 5 astronomical treatises, synthesizing the knowledge from various schools of thought. It included the Surya Siddhanta, Romaka Siddhanta, Polisha Siddhanta, Vasishta Siddhanta, and Paitamaha Siddhanta. The Panchasiddhantika was a testament to Varamihira's deep understanding and mastery of astronomy, and it provided invaluable insights into the astronomical practices of his era. But Varamihira's contributions were not confined to astronomy alone. He also made significant strides in astrology, an integral part of Indian culture and tradition. His most famous work in this field is the Brihat Samhita, a vast encyclopedia that covered a wide range of topics, from astrology and astronomy to architecture and even gemology. The Brihat Samhita was a reflection of Varahimira's encyclopedic knowledge and his ability to connect diverse fields of study. In the realm of astrology, Varahimira's contributions were unmatched. He provided detailed descriptions of planetary motions, lunar and solar eclipses, and their influence on human affairs. His astrological predictions and the interpretations were based on the meticulous observations and calculations, blending scientific rigor with traditional beliefs. Varahimira's work had a profound impact on later astronomers and astrologers. His innovative methods and comprehensive approach set new standards in the field. He introduced the concept of hora, an hour in astrology, which became a cornerstone of astrological practices. His influence extended beyond the borders of India as his works were studied and revered by scholars in the Islamic world and later in Europe. Varahimira's legacy is not just confined to his scholarly achievements, it also lies in the inspiration he provided to countless generations of astronomers and astrologers. His works have been preserved and studied for centuries, a testament to their enduring relevance and significance. Now let's travel back to the 7th century CE and meet one of the most brilliant minds of ancient India, Brahmagupta. Born in 598 CE in the region of Binmal in modern-day Rajasthan, Brahmagupta was destined to become one of the greatest mathematicians and astronomers of his time. Brahmagupta grew up in a society where astronomy and mathematics were not just academic pursuits, but integral parts of daily life. From a young age, he showed a natural aptitude for numbers and the stars. He was deeply fascinated by the mysteries of the cosmos and the mathematical principles that governed them. His journey of discovery and innovation was just the beginning. As Brahmagupta matured, his work began to take shape in the form of his magnum opus, the Brahmasputa Siddhanta, written around 628 CE. This monumental text, composed in Sanskrit, was a treasure trove of astronomical knowledge and mathematical theories. It covered a wide range of topics, from planetary motions and lunar eclipses to algebraic equations and geometric principles. Brahmasputa Siddhanta was a groundbreaking work that laid the foundation for many future discoveries. One of Brahmagupta's most remarkable contributions was his work on gravity. Long before Sir Isaac Newton's famous apple incident, Brahmagupta had already theorized about the force that causes objects to fall to the ground. He proposed that there is a force of attraction that pulls objects towards the Earth, a concept that was revolutionary for his time. Although his explanation differed from Newton's law of gravitation, Brahmagupta's insights were a significant step forward in understanding the forces that govern our world. Brahmagupta was also a master of eclipse prediction. He meticulously observed the movements of the sun and the moon, and his calculations allowed him to predict both solar and lunar eclipses with remarkable accuracy. He understood that the lunar eclipses occurred when the moon passed into the Earth's shadow, and solar eclipses happened when the moon obscured the sun. His work in this area was detailed in the Brahmasputa Siddhanta and showcased his profound understanding of celestial mechanics. He also wrote another significant work, the Khanda Kadyaka, which further expanded of his astronomical theories and provided practical guidelines for astronomical observations. This text was a vital resource for astronomers of his time and for generations to come. It included tables and calculations that helped in predicting the positions of planets and stars, making it an invaluable tool for celestial navigation and astrology. In addition to his work on gravity and eclipses, Brahmagupta made significant advances in the field of mathematics. He introduced the concept of zero as a number and used it in calculations, which was a revolutionary idea that transformed mathematics. He also worked on solving quadratic equations and developed methods for dealing with negative numbers, all of which were groundbreaking for his time. Brahmagupta's life and work were a testament to his brilliance and his relentless pursuit of knowledge. His contributions to the fields of astronomy and mathematics have left an enduring legacy, influencing scholars and scientists for centuries. As we reflect on his achievements, we are reminded of the profound impact that one individual's curiosity and intellect can have on the world. The story of Brahmagupta is a fascinating journey through the cosmos and the world of numbers, a journey that continues to inspire and captivate us to this day. Now let's meet Bhaskara I, an exceptional mathematician and astronomer from ancient India. Bhaskara I was born in 600 CE, and his remarkable journey of intellectual pursuit began in a small village in what is now modern-day India. From a young age, Bhaskara I displayed an extraordinary aptitude for mathematics and astronomy. His curiosity and keen observational skills set him apart from his peers. As he grew older, his passion for understanding the mysteries of the cosmos deepened, and he dedicated his life to studying the intricate workings of the universe. Bhaskara I's most significant contributions are encapsulated in his two major works, the Mahabhaskariya and the Laghu Bhaskariya. These texts are a masterpiece that showcases his profound understanding of mathematics and its application in astronomy. The Mahabhaskariya, or the Great Book of Bhaskara, is a comprehensive treatise on astronomy. In this works, Bhaskara first meticulously detailed the motions of celestial bodies, the calculations of planetary positions, and the prediction of eclipses. His precise and methodical approach to these complex topics demonstrated his exceptional analytic skills. His insights into the movements of the planets and the calculation of their positions were revolutionary for his time. He developed innovative methods to determine the position of the sun, moon, and the planets at any given time. These calculations were essential for astronomical observations and had practical applications in astrology and navigation. One of Bhaskara I's groundbreaking contributions to mathematics was his works on trigonometry. In the Mahabhaskariya, he introduced and refined trigonometric concepts that would later become fundamental to the field. His work on sine and cosine functions, as well as their applications in calculating the positions of celestial bodies, were really noteworthy. Bhaskara I's other major work, the Laghu Bhaskariya, or the smaller Book of Bhaskara, is a concise yet comprehensive text on astronomy. This work serves as practical guide for astronomers, providing simplified methods for calculating planetary positions and predicting eclipses. The Laghu Bhaskariya was widely used for astronomers and scholars for centuries, attesting to its lasting impact. One of the most remarkable aspects of Bhaskara I's work was his ability to connect mathematical theories with practical applications. He demonstrated how trigonometric functions could be used to solve real-world problems, such as determining the distance between celestial bodies and predicting the timing of eclipses. His work laid the foundation for future advancements in both mathematics and astronomy. Now let's move to Bhaskara II. Born in 1114 CE in the village of Vijayavadiva, present-day Bijapur, Karnataka, Bhaskara II was destined to become one of the greatest mathematicians and astronomers of all time. As a young boy, Bhaskara II was surrounded by an environment that fostered intellectual curiosity. His father, Mahesvara, was a renowned scholar and astronomer who played a crucial role in nurturing his son's talent. Bhaskara II's early education was steeped in the rich tradition of Indian mathematics and astronomy. It wasn't long before his own genius began to shine. Bhaskara II's contributions to the world of mathematics and astronomy are immortalized in his major works, the most notable being Siddhanta Shiromani, Lilavati, and Bijaganita. The Siddhanta Shiromani, which translates to the crown of the treatise, is an extraordinary compendium divided into 4 parts: Lilavati, arithmetic; Bijaganita, algebra; Grahaganita, planetary mathematics; and Goladhyaya, sphere. This monumental work covers a vast array of mathematical and astronomical topics, showcasing Bhaskara II's deep understanding and mastery of these subjects. The Lilavati, named after Bhaskara's second beloved daughter, is a treatise on arithmetic that is both practical and poetic. Legend has it that Bhaskara II wrote this book to console his daughter, whose marriage was tragically delayed by a miscalculated time. The Lilavati is filled with engaging problems and solutions, presented in a way that captivates the reader's imagination. Bhaskara II's ability to make complex mathematical concepts accessible and enjoyable is a testament to his brilliance as a teacher. In Bijaganita, covering algebra, Bhaskara II delves into the world of algebra, introducing innovative methods for solving equations and dealing with positive and negative numbers. His work on indeterminate equations, specifically the Chakravala method, was groundbreaking and influenced future generations of mathematicians mathematicians. Bhaskara II's algebraic techniques laid the foundation of modern algebra and demonstrated his profound mathematical insight. Bhaskara II's contributions to calculus were also remarkable. Long before the European mathematician Isaac Newton developed his theories, Bhaskara II had already made significant strides in this field. In the Siddhanta Shiromani, he presented concepts similar to differential calculus, including the notion of infinitesimals and derivatives. His work on the rate of change and principles of calculus was applied to various astronomical calculations, demonstrating its practical utility. One of Bhaskara II's most fascinating contributions was his concept of gravitational force. In the Goladhyaya section of the Siddhanta Shiromani, he proposed that objects fall to the ground due to a force of attraction exerted by the Earth. This idea was a precursor to the concept of gravity later formulated by Isaac Newton. Although Bhaskara II's explanation differed from Newton's, his insights were a significant step towards understanding the force that governed the motion of objects. Bhaskara II's work on planetary motion and eclipses was equally impressive. He developed methods to predict the positions of planets and calculate the timing of solar and lunar eclipses with remarkable accuracy. His keen observations and mathematical prowess allowed him to create detailed astronomical tables that were used by scholars for centuries. The legacy of Indian astronomy stretched far beyond its borders, influencing astronomers across different cultures and eras. As time progressed, the profound contributions of Indian astronomers like Aryabhata, Brahmagupta, and Bhaskara II began to resonate beyond the subcontinent. Their works were not only preserved, but also enriched the astronomical knowledge of later Indian scholars. These luminaries built upon the foundations laid by their predecessors, creating a continuous thread of astronomical brilliance. Meanwhile, the Islamic world was experiencing its own golden age of science and learning. As the Islamic Empire expanded, it came into contact with the rich intellectual heritage of India. Scholars in places like Baghdad, known for its House of Wisdom, eagerly sought out knowledge from different cultures. The works of Indian astronomers were among the prized treasures that these scholars embraced. One of the key figures in this cross-cultural exchange was the Persian scholar Al-Khwarizmi, who lived in the 9th century. Al-Khwarizmi is often considered the father of algebra, and he was profoundly influenced by the mathematical and astronomical knowledge of ancient India. His work, Zij al-Sindind, drew heavily from Indian astronomical texts, especially those of Brahmagupta. Al-Khwarizmi's contributions to mathematics and astronomy were instrumental in shaping the scientific landscape of the Islamic world. The preservation of Indian astronomical texts were greatly facilitated by the translation efforts of Islamic scholars. These scholars translated important works from Sanskrit into Arabic, ensuring that the knowledge would endure and spread. For instance, Brahmagupta's Brahmasputa Siddhanta was translated into Arabic and became known as Sindind al-Kabir. This translation played a crucial role in transmitting Indian astronomical ideas to the Islamic world. The influence of Indian astronomy extended even further through the work of scholars like Al-Biruni, an 11th century polymath who traveled to India and immersed himself in its culture and sciences. Al-Biruni's deep appreciation for Indian knowledge led him to write extensively about Indian astronomy and mathematics. His work, Kitab al-Hind, provided valuable insights into Indian scientific achievements and helped bridge the gap between different cultures. The ripple effect of this exchange didn't stop in the Islamic world. The knowledge preserved and enriched by Islamic scholars eventually found its way to medieval Europe. During the Renaissance, European scholars rediscovered these ancient texts, which had been translated from Arabic into Latin. This reintroduction of Indian astronomical and mathematical knowledge significantly contributed to the scientific revolution in Europe. It's fascinating to see how the brilliance of ancient Indian astronomy transcended geographical and cultural boundaries, influencing generations of scholars and astronomers. The collaborative spirit of knowledge sharing between India and Islamic scholars ensured that these valuable insights would continue to illuminate the path of discovery for centuries to come. This narrative showcases the remarkable journey of Indian astronomical knowledge, from its origins in the Indian subcontinent to its profound impact on the Islamic world and beyond. It's a testament to the enduring power of human curiosity and the interconnectedness of our shared intellectual heritage. As our journey through the history of ancient Indian astronomy comes to an end, let's reflect on the brilliance of the scholars we've met. From Aryabhata's precise calculations to Brahmagupta's work on gravity and Bhaskara II's contributions to calculus, these luminaries shaped the way we understand the cosmos. Their discoveries laid the groundwork for many modern scientific principles and continue to inspire scholars today. The relevance of their work is evident in the way it influenced not only Indian astronomy, but also the broader scientific community across cultures and eras. eras. Their legacy reminds us of the power of curiosity, observation, and the relentless pursuit of knowledge. As we look up at the stars tonight, let's remember the wisdom of these ancient astronomers and their enduring contributions to the field of astronomy. The stars are not just distant points of light, they are a testament to the shared human quest to understand the universe. The Islamic Golden Age, spanning from the 8th to the 14th century, was a period of remarkable intellectual and cultural flourishing in the Islamic world. During this era, scholars made significant advancements in various fields, including mathematics, medicine, philosophy, and notably astronomy. The Islamic Golden Age saw the rise of great cities like Baghdad, Cairo, and Cordoba, which became centers of learning and innovation. It was a time when knowledge from different cultures was eagerly sought, preserved, and expanded upon. Astronomy held a special place during the Islamic Golden Age. Islamic scholars were deeply motivated to study the heavens for both practical and religious reasons. One of the primary motivations was the need to accurately determine the direction of Mecca for prayer, as well as to establish the Islamic lunar calendar. This practical necessity drove astronomers to develop sophisticated methods for observing and calculating celestial movements. Islamic astronomers made significant contributions to the field, such as refining the astrolabe, developing new astronomical tables, and making precise observations of celestial bodies. These advancements were not just theoretical, but had practical applications in navigation, timekeeping, and agriculture. The establishment of observatories in cities like Baghdad and Samarkand further propelled the study of astronomy. The importance of astronomy during this period cannot be overstated. It was a field that bridged the gap between science and religion, practicality and theory. The meticulous work of Islamic astronomers laid the groundwork for future discoveries and had a lasting impact on the scientific community. Their contributions are a testament to the Islamic Golden Age's enduring legacy in the history of astronomy. During the Islamic Golden Age, one of the most remarkable achievements was the preservation and translation of ancient Greek texts. This period saw an unprecedented commitment to the collection, translation, and dissemination of knowledge from diverse cultures. The Islamic world became a melting pot of intellectual pursuits, where scholars actively sought to preserve and expand upon the works of earlier civilizations. The translation movement began under the Abbasid Caliphate, particularly during the reign of Caliph Harun al-Rashid and his son, Caliph al-Mamun. Al-Mamun established the Bait al-Hikmah, or House of Wisdom, in Baghdad around the 9th century. This institution served as a major center of learning and translation, attracting scholars from various parts of the Islamic world and beyond. The House of Wisdom became a hub for translating Greek, Persian, Indian, and other texts into Arabic. The preservation of Greek astronomical texts was of particular importance to Islamic scholars. They recognized the immense value of the works of renowned Greek astronomers such as Ptolemy, Aristotle, and Hipparchus. These texts contain detailed observations, calculations, and theories that form the foundation of classical astronomy. By translating these works into Arabic, Islamic scholars ensured that this invaluable knowledge was not lost to the ravages of time. The translation process was meticulous and required a deep understanding of both the source and the target language. Scholars like Hunayn ibn Ishaq and Thabit ibn Qurra played pivotal roles in this endeavor. Hunayn ibn Ishaq, a renowned translator, translated numerous Greek texts, including Ptolemy's Almagest, into Arabic. Thabit ibn Qurra, another prominent figure, not only translated but also critically examined and expanded upon the Greek works. One of the significant contributions of Islamic scholars was their approach to translating these texts. They did not merely translate word for word. Instead, they engaged with the material, critically analyzed it, and often made improvements and corrections. This rigorous approach led to the development of new ideas and the refinement of existing theories. The translations were not static but dynamic, reflecting the active intellectual engagement of Islamic scholars with the ancient knowledge. The impact of this translation movement extended beyond the Islamic world. The translated works were eventually transmitted to Europe, where they played a crucial role in the Renaissance and the scientific revolution. European scholars such as Gerard of Cremona translated the Arabic versions of Greek texts into Latin, making them accessible to a wider audience. The preservation and dissemination of Greek astronomical knowledge by Islamic scholars thus bridged the gap between the ancient and the modern world. In addition to preserving Greek texts, Islamic scholars made their own significant contributions to astronomy. They built upon the foundations laid by the Greeks and developed new astronomical models, improved instruments, and more accurate observations. The integration of Greek knowledge with Islamic innovation created a rich tapestry of astronomical understanding that would influence generations to come. The preservation and translation of Greek texts during the Islamic Golden Age exemplified the the dedication of Islamic scholars to the pursuit of knowledge. Their efforts not only safeguarded the intellectual heritage of ancient civilizations, but also paved the way for future advancements in science and astronomy. This remarkable period of intellectual cross-pollination underscores the importance of cultural exchange and the enduring legacy of the Islamic Golden Age in the history of human knowledge. During the Islamic Golden Age, one of the key factors that propelled astronomical studies to the new heights was the development and refinement of astronomical instruments. Islamic astronomers were not only scholars, but also skilled craftsmen who created and improved devices that allowed for more precise observations of the heavens. One of the most significant advancements was in the design and use of astrolabe. The astrolabe, an ancient Greek innovation, was vastly improved by Islamic scholars. It became a multifunctional instrument used for solving problems related to timekeeping, navigation, and the measurement of celestial objects. With its intricate design, the astrolabe allowed astronomers to measure the altitude of stars above the horizon, determine the time of day or night, and even find the direction of Mecca for prayer. Scholars like Al-Fazari and Al-Batani made substantial contributions to the development of more advanced and accurate astrolabes. Another pivotal instrument that saw advancements during this period was the quadrant. The quadrant was a quarter-circle panel used to measure the altitude of celestial objects. Islamic astronomers improved its design, making it more precise and easier to use. This instrument was crucial for astronomical observations and navigation, allowing for more accurate measurements of the positions of stars and planets. The armillary sphere was yet another instrument that Islamic astronomers refined. This model of celestial sphere, consisting of a series of rings representing the great circles of the heavens, was used to demonstrate the apparent motions of stars around the Earth. Islamic scholars like Al-Farghani and Al-Sufi enhanced the armillary sphere, making it a vital tool for teaching and understanding celestial mechanics. Islamic astronomers also made strides in the construction and use of observatories. Observatories in cities like Baghdad and Samarkand were equipped with state-of-the-art instruments and served as centers for astronomical research and education. These observatories provided a dedicated space for systematic observations and the recordings of celestial phenomena. The Marogeh Observatory, founded by Nasir al-Din al-Tusi in the 13th century, is one notable example. It housed an impressive array of instruments, including a large wall quadrant and an armillary sphere, enabling astronomers to make precise measurements and calculations. One innovative instrument developed during this period was the sextant, an early version of which was used by Islamic astronomers to measure the angular distances between celestial objects. The sextant's design evolved over time, eventually becoming a crucial tool for navigation and astronomy. In addition to these instruments, Islamic astronomers also made advancements in the production of astronomical tables, known as zich. These tables contained comprehensive data on the positions of celestial bodies, solar and lunar eclipses, and other astronomical phenomena. The advancements in astronomical instruments during the Islamic Golden Age were instrumental in expanding our understanding of the cosmos. These tools enabled Islamic scholars to make more accurate observations, develop new theories, and refine existing knowledge. The legacy of these innovations continues to influence modern astronomy, highlighting the enduring impact on the field. In the rich tapestry of the Islamic Golden Age, Al-Fazari stands out as a pivotal figure in the field of astronomy. His work not only advanced the understanding of celestial phenomena, but also laid the groundwork for future scholars. Al-Fazari, whose full name was Muhammad ibn Ibrahim al-Fazari, was a Persian scholar who lived in the 8th century. He is often celebrated as one of the earliest Islamic astronomers and mathematicians, and his contributions to the field have left an enduring legacy. Al-Fazari's interest in astronomy was deeply intertwined with his work in mathematics. He understood that precise mathematical calculations were essential for accurate astronomical observations. One of his significant contributions was his role in translating and enhancing the knowledge inherited from previous civilizations. Al-Fazari translated important Greek and Indian astronomical texts into Arabic, making this knowledge accessible to the Islamic world. His translations played a crucial role in preserving and disseminating the astronomical wisdom of ancient cultures. Among his notable works is his translation of the Sindhin, an astronomical text of Indian origin. This text, originally known as the Siddhanta, was a comprehensive treatise on astronomy and mathematics. Al-Fazari's translation, along with his commentary and enhancements, introduced sophisticated astronomical concepts to the Islamic world. The Sindhind provided detailed information on planetary movements, lunar and solar eclipses, and other celestial phenomena. Al-Fazari's work on this text demonstrated his deep understanding of both the theoretical and practical aspects of astronomy. Al-Fazari's contributions extended beyond translations. He was also an innovator who developed new instruments and methods for astronomical observations. One of his significant achievements was his work on the astrolabe. While the astrolabe was an ancient Greek innovation, Al-Fazari refined and improved its design, making it more accurate and versatile. His enhancements allowed astronomers to measure the altitude of celestial bodies more precisely and facilitated various calculations related to timekeeping and navigation. In addition to his work on astrolabe, Al-Fazari was instrumental in the development of armillary sphere, another critical astronomical instrument. The armillary sphere, with its series of rings representing the celestial circles, was used to model the apparent movements of stars and planets. Al-Fazari's improvements to the armillary sphere made it a more effective tool for teaching and understanding the mechanics of the heavens. Al-Fazari's influence extended to his role as a teacher and mentor. He was part of the intellectual circle that flourished under the patronage of Abbasid Caliphate. His teachings inspired a generation of scholars who would go on to make their own significant contributions to astronomy and other sciences. Al-Fazari's legacy can be seen in the work of later astronomers like Al-Battani, who built upon the foundations laid by their predecessors. One of the hallmarks of Al-Fazari's approach to astronomy was his emphasis on empirical observation and mathematical precision. He believed that accurate data collection and rigorous calculations were essential for understanding the cosmos. This approach was a departure from the more speculative and philosophical methods of earlier astronomers and set a standard for scientific inquiry that would influence future generations. Al-Fazari's contributions to astronomy during the Islamic Golden Age were instrumental in advancing the field and bridging the gap between the ancient knowledge and the new discoveries. His work exemplifies the spirit of intellectual curiosity and innovation that defined this remarkable period. Through his translations, instrument development, and mentorship, Al-Fazari left an indelible mark on the history of astronomy, ensuring that knowledge of the heavens would continue to evolve and inspire future generations. Al-Battani, also known as Albatanius in the Latin world, was a renowned Islamic astronomer and mathematician who lived during the late 9th century and early 10th century. His full name was Abu Abdallah Muhammad ibn Jabir ibn Sinan al-Raqi al-Harani al-Sabi al-Battani. Born in Haran, a city in what is now southeastern Turkey, Al-Battani made significant contributions to the field of astronomy that have had a lasting impact on the scientific community. One of Al-Battani's most notable achievements was his improvement of Ptolemaic astronomy. He critically analyzed Ptolemy's work, particularly the Almagest, and corrected several of his errors. Al-Battani's observations and calculations were remarkably precise for his time, and he made significant advancements in understanding the movements of celestial bodies. His work included the measurement of the length of the solar year, which he calculated to be 365 days, 5 hours, 46 minutes and 24 seconds, a value that is remarkably close to the modern measurement. Al-Battani's most famous work, the Kitab al-Zij, also known as the Sabian Tables or the Book of Tables, was a comprehensive astronomical treatise. In this work, he compiled extensive astronomical data, including the position of stars and planets, as well as tables for calculating the positions of celestial bodies. The Kitab al-Zij became a highly influential text, widely used by astronomers in both the Islamic world and Europe. It provided a more accurate and detailed understanding of the heavens, serving as a valuable resource for future generations of astronomers. Another significant contribution of Al-Battani was his work in trigonometry, which played a crucial role in advancing astronomical calculations. He introduced the use of sine and tangent functions, replacing the previously used by Greek chord method. Al-Battani's development of trigonometric functions allowed for more precise and efficient calculations of celestial positions. His work in this area laid the groundwork for the development of modern trigonometry and its applications in various scientific fields. Al-Battani's contributions extended to the observation and prediction of lunar and solar eclipses. He meticulously recorded the timings and positions of eclipses, providing valuable data for future astronomers. His accurate predictions of eclipses demonstrated his deep understanding of celestial mechanics and his ability ability to apply mathematical principles to astronomical phenomena. In addition to his observational and theoretical work, al-Battani made significant improvements to astronomical instruments. He refined the design of astrolabe, making it more accurate and versatile. His enhancements allowed astronomers to measure the altitude of celestial bodies with greater precision, aiding in navigation and timekeeping. Al-Battani also worked on the development of sundials and other timekeeping devices, contributing to the accurate measurement of time based on the position of the sun. Al-Battani's influence extended beyond his lifetime. As his works were translated into Latin and studied by European scholars during the Renaissance, his Kitab az-Zij was translated by Gerard of Cremona and became a standard reference for astronomers in medieval Europe. The accuracy and comprehensiveness of al-Battani's data made his work a cornerstone of astronomical studies, bridging the gap between ancient Greek astronomy and the scientific advancements of the Renaissance. The legacy of al-Battani is a testament to the intellectual rigor and innovative spirit of the Islamic Golden Age. His contributions to astronomy, trigonometry, and the development of astronomical instruments have had a profound and lasting impact on the field. Al-Battani's work exemplifies the synthesis of observation, mathematical precision, and critical analysis that characterize the scientific achievements of this remarkable period. His enduring influence continues to inspire and inform the study of the cosmos today. Al-Khwarizmi, often hailed as the father of algebra, was a pioneering Islamic scholar whose contributions during the Islamic Golden Age extended far beyond mathematics. His full name was Muhammad ibn Musa al-Khwarizmi, and he lived during the 9th century, primarily in Baghdad. Al-Khwarizmi's work in mathematics, astronomy, and geography had a profound impact on the intellectual landscape of his time and laid the groundwork for many future advancements. Al-Khwarizmi's interest in astronomy was closely linked to his mathematical pursuit. He understood that accurate astronomical observations required precise mathematical calculations. One of his most significant contributions was the development of trigonometric tables that were essential for astronomical calculations. These tables included values for sine and tangent functions, which allowed astronomers to make more accurate predictions of celestial events and positions of stars and planets. Al-Khwarizmi's work in trigonometry laid the foundation for future astronomers and mathematicians to build upon. In addition to his work on trigonometric tables, Al-Khwarizmi made substantial contributions to the field of astronomical geography. He authored a comprehensive work titled Kitab Surat al-Ard, the book of the description of the Earth, which provided detailed information about the geographical locations of various cities and regions. This work was based on the Ptolemaic model but included corrections and updates based on more accurate observations. Al-Khwarizmi's geographical work was instrumental in improving the accuracy of maps and understanding the spatial relationships between different regions. One of Al-Khwarizmi's most notable achievements in astronomy was his work on the Zij al-Sindind, an astronomical treatise that provided extensive tables and calculations for predicting the positions of celestial bodies. This work was based on Indian astronomical knowledge and was one of the earliest and most influential Zij produced in the Islamic world. The Zij al-Sindind included data on the movements of the sun, moon, and the planets, as well as calculations for determining the times of lunar and solar eclipses. Al-Khwarizmi's meticulous work on these tables set a high standard for future astronomers and was widely used for centuries. Al-Khwarizmi's contributions to astronomy were not limited to theoretical work. He also made significant advancements in the development of astronomical instruments. He improved the design of the astrolabe, an ancient Greek instrument used for measuring the altitude of celestial bodies and solving problems related to timekeeping and navigation. Al-Khwarizmi's enhancements to astrolabe made it more accurate, versatile, allowing astronomers to perform a wider range of calculations with much greater precision. Another important aspect of Al-Khwarizmi's work was his role in the translation and preservation of ancient knowledge. He was part of the House of Wisdom in Baghdad, an intellectual center where scholars translated and expanded upon the works of earlier civilizations. Al-Khwarizmi translated Greek and Indian astronomical texts into Arabic, making this knowledge accessible to the Islamic world. His translations and commentaries enriched the intellectual heritage of the time and ensured that valuable astronomical knowledge was preserved for future generations. Al-Khwarizmi's legacy in astronomy is a testament to his dedication to the pursuit of knowledge and his ability to integrate mathematical precision with empirical observation. His contributions laid the groundwork for many of the advancements in astronomy during the Islamic Golden Age and had a lasting impact on the field. The influence of his work can be seen in the development of later astronomers, both in the Islamic world and in Europe, where his works were translated and studied during the Renaissance. The Islamic Golden Age was marked by numerous significant advancements in the field of astronomy. Islamic astronomers made groundbreaking discoveries and developed innovative theories that profoundly impacted our understanding of the cosmos. Their meticulous observations, mathematical precision, and critical analysis led to major astronomical achievements that continue to influence modern science. One of the most notable achievements during this period was the refinement of the Ptolemaic model of the universe. The Ptolemaic model, which described the geocentric arrangement of celestial bodies, was the dominant astronomical framework inherited from the Greeks. Islamic astronomers such as al-Battani and Ibn al-Shatir critically examined and improved upon this model. Al-Battani's precise measurements of the solar year and the orbits of planets led to the corrections in Ptolemy's calculations, making the model more accurate. Ibn al-Shatir further refined the Ptolemaic system by introducing the concept of secondary epicycles, which provided a better explanation of the observed planetary motions. Another major achievement was the development of accurate astronomical tables known as zich. These tables contained comprehensive data on the positions of celestial bodies, lunar and solar eclipses, and other astronomical phenomena. The zich compiled by al-Battani, known as the Albaitinius tables, and the Toledian tables, created by al-Zarqali, were among the most influential. These tables were used by astronomers for centuries and played a crucial role in advancing our understanding of celestial mechanics. Islamic astronomers also made significant contributions to the study of lunar and solar eclipses. They developed methods for predicting the timings and positions of eclipses with remarkable accuracy. Al-Biruni, for example, provided detailed descriptions of both lunar and solar eclipses, including the conditions under which they occur. His work in this area helped improve the accuracy of eclipse predictions and provided valuable data for future astronomers. The study of planetary motion was another area where Islamic astronomers excelled. They developed sophisticated models to describe the movements of planets and their orbits. Al-Tusi, a prominent astronomer, introduced the Tusi couple, a geometric model that explained the apparent motion of planets without relying on the Ptolemaic epicycles. This innovative model was later used by Copernicus in developing the heliocentric theory of the solar system. The Islamic Golden Age also saw the establishment of the observatories, which played a critical role in advancing astronomical research. The Marogeh Observatory was one of the most famous. Equipped with the state-of-art instruments, the observatory provided a dedicated space for systematic observation and the recording of celestial phenomena. The observatory's staff compiled extensive astronomical data which contributed to the development of more accurate models of the universe. Islamic astronomers made significant advancements in the development of astronomical instruments as well. They refined the design of the astrolabe, making it more accurate and versatile. The astrolabe was used for various purposes, including measuring the altitude of celestial bodies, determining the time of day or night, and finding the direction of Mecca for prayer. Islamic scholars also improved the design of quadrants, sextants, and armillary spheres, enhancing their precision and utility in astronomical observations. In addition to these achievements, Islamic astronomers made important contributions to the field of timekeeping. They developed sophisticated methods for measuring time based on the position of celestial bodies. Al-Biruni's work on the determination of Earth's radius and circumference, as well as his development of accurate calendars, demonstrated the practical applications of astronomical knowledge in daily life. The major astronomical achievements of the Islamic Golden Age were characterized by a commitment to empirical observation, mathematical rigor, and intellectual curiosity. Islamic astronomers bridged the gap between the ancient Greek knowledge and modern scientific discoveries, leaving a lasting legacy that continues to shape our understanding of the cosmos. Their contributions exemplify the spirit of innovation and dedication to the pursuit of knowledge that defined this remarkable period in history. The legacy of the Islamic Golden Age in astronomy is profound and far-reaching. Islamic scholars' meticulous work during this period laid the groundwork for many of the astronomical principles and practices we rely on today. Their contributions have had a lasting impact, shaping modern astronomy and influencing scientific thought across various disciplines. One of the most significant legacies of the Islamic Golden Age is the preservation and expansion of ancient knowledge. Islamic scholars translated and preserved key astronomical texts from Greek, Indian, and Persian sources, ensuring that this valuable knowledge was not lost to history. By critically analyzing, improving, and expanding upon these texts, they created a rich intellectual environment that fostered innovation and discovery. This preservation of knowledge was crucial for later developments in astronomy during the Renaissance and the Scientific Revolution. The influence of Islamic astronomy extended to the realm of theoretical advancements as well. Islamic scholars challenged and refined the Ptolemaic model of the universe, introducing new concepts and corrections that improved its accuracy. The work of Ibn al-Shatir, who developed the Tusi couple to explain planetary motion, was later used by Copernicus in his formulation of the heliocentric model. This connection highlights the direct influence of Islamic astronomical thought and development of modern scientific theories. Islamic astronomers also made significant contributions to the understanding of timekeeping and the calendar. Their work on the Islamic lunar calendar, based on precise observations of the moon's phases, provided a model for accurate time measurement. The development of accurate calendars and timekeeping methods was essential for religious, agricultural, and navigational purposes. These innovations continue to influence modern timekeeping systems and the study of celestial mechanics. The legacy of the Islamic Golden Age in astronomy is not just limited to the scientific advancements made during that period. It also encompasses the spirit of intellectual curiosity, critical analysis, and interdisciplinary scholarship that defined this remarkable era. The integration of knowledge from diverse cultures, the commitment to empirical observation, and the pursuit of mathematical precision set a standard for scientific inquiry that continues to inspire researchers today. In conclusion, the contributions of Islamic astronomers during the Islamic Golden Age were monumental in shaping our understanding of the cosmos. Their work in preserving and translating ancient texts, developing sophisticated astronomical instruments, and making groundbreaking discoveries has left an indelible mark on the field of astronomy. Scholars like Al-Fazari, Al-Batani, and Al-Khwarizmi exemplify the spirit of intellectual curiosity and innovation that defined this remarkable period. The meticulous observations and mathematical precision of Islamic astronomers laid the foundation for many of the principles and practices that modern astronomy relies on today. Their advancements in trigonometry, development of astronomical tables, and refinement of the Ptolemaic model significantly improved our understanding of celestial mechanics. The establishment of observatories provided dedicated spaces for systematic study and data collection, further advancing the field. The legacy of the Islamic Golden Age is not only found in the scientific advancements made during that time, but also in the approach to knowledge itself. Islamic scholars demonstrated the importance of cultural exchange, critical analysis, and interdisciplinary scholarship. Their willingness to engage with and build upon the knowledge of previous civilizations created a rich intellectual environment that fostered progress and discovery. As we reflect on the achievements of Islamic astronomers, we are reminded of the enduring power of knowledge and the importance of preserving and expanding upon the wisdom of the past. The contributions of the Islamic Golden Age continue to inspire and inform the study of the cosmos, highlighting the timeless value of intellectual curiosity and the pursuit of understanding. By appreciating the work of these pioneering scholars, we honor their legacy and recognize the profound impact they have had on the history of astronomy and science as a whole. The Islamic Golden Age serves as a testament to the remarkable achievements that can be made when cultures come together in the shared pursuit of knowledge and discovery. Let's journey through the medieval Europe, a period often overshadowed by the brilliance of the Renaissance that followed. However, it's essential to recognize that the medieval period was not a dark age for astronomy. Instead, it was a time of significant advancements and contributions by European astronomers who laid the groundwork for future discoveries. Our focus today is on the development of astrolabes and the remarkable work of scholars like John of Sacro Bosco. The medieval period, spanning roughly from the 5th to the late 15th century, was a time of great intellectual exchange and growth. With the fall of the Roman Empire, Europe became a melting pot of knowledge, drawing from the rich legacies of ancient Greece and Rome, as well as the groundbreaking works of Islamic scholars during the Islamic Golden Age. This period saw the establishment of monastic schools and universities, which played a crucial role in preserving and advancing astronomical knowledge. Astrolabes, intricate instruments used for solving problems related to the time and the position of the stars, became a symbol of medieval astronomical ingenuity. These devices were not only practical tools for navigation and timekeeping, but also masterpieces of craftsmanship and scientific understanding. The development and refinement of astrolabes in Europe showcased the dedication and skill of medieval astronomers, who continually improved upon the designs they inherited from earlier civilizations. One of the most influential figures of this period was John of Sacro Bosco, a scholar whose work left an indelible mark on the field of astronomy. Born around 1195, Sacro Bosco was a mathematician and astronomer who authored several key texts, including the Sphera Mundi. This work became a cornerstone of medieval astronomical education, offering a clear and concise explanation of the Ptolemaic system and the movements of celestial bodies. The importance of the medieval period in the history of astronomy cannot be overstated. It was a time of preservation, adaptation, and innovation, where the knowledge of the ancients was not merely kept alive but actively enhanced. The work of European astronomers during this time, including the development of astrolabes and contributions of John Sacrobosco, set the stage for astronomical revolution that would come with the Renaissance. This episode will delve into the fascinating developments, highlighting the enduring legacy of medieval European astronomy. The medieval period in Europe, stretching from the 5th to the late 15th century, is often mistakenly characterized as a dark age for intellectual pursuits. However, this era was a crucible of cultural and scientific exchange, profoundly shaping the development of astronomy. The astronomical knowledge that flourished during this period was profoundly influenced by the legacies of ancient civilizations and the remarkable contributions of scholars from the Islamic Golden Age. When the Western Roman Empire fell in the 5th century, Europe experienced significant downfall. However, pockets of learning persisted, and the preservation of knowledge became a vital endeavor. Monastic schools and later universities emerged as key institutions in this mission. Monasteries in particular played a crucial role in maintaining and copying ancient texts, including astronomical works from Greek and Roman sources. This period also saw the translation movement, which brought a wealth of knowledge from the Islamic world to Europe. The Islamic Golden Age, spanning from the 8th to the 14th centuries, was a period of unparalleled intellectual achievements in the Islamic world. Scholars like Al-Khwarizmi and Al-Battani made groundbreaking contributions to astronomy, mathematics, and optics. Their works were meticulously recorded in Arabic and later translated into Latin, becoming essential texts for European scholars. The transfer of this knowledge was facilitated by the Crusades, trade, and the Reconquista, which opened channels of communication between the Islamic world and Europe. Translations of key astronomical texts such as Ptolemy's Almagest and Al-Battani's De Scientia Stellarum were pivotal in shaping medieval European astronomy. These works provided a comprehensive understanding of the Ptolemaic system, which described the geocentric model of the universe. European scholars eagerly embraced these translations, incorporating them into their studies and teaching. Monastic schools and universities became the epicenters of intellectual revival. Monasteries, with their scriptoriums, were instrumental in preserving and disseminating astronomical knowledge. They copied manuscripts, ensuring the survival of ancient and Islamic works. Universities, which began to flourish in the 12th century, became hubs of learning and scholarship. The University of Paris in particular emerged as a prominent center for astronomical studies. The establishment of universities marked a significant shift in the dissemination of knowledge. These institutions fostered a scholarly community that valued inquiry and debate. Astronomy was integrated into quadrivium, the advanced curriculum of the medieval university, alongside arithmetic, geometry, and music. This formal education system allowed for a systematic study of celestial phenomena and the refinement of astronomical theories. The historical context of medieval Europe thus set the stage for significant advancements in astronomy. The synthesis of ancient, Islamic, and contemporary knowledge created a fertile ground for innovation. European astronomers, building on this rich legacy, made substantial contributions that would eventually pave the way for scientific revolution of the Renaissance. The astrolabe is one of the most fascinating and versatile instruments in the history of astronomy. It is an ancient tool used to solve problems related to time and the position of celestial bodies, and its development and refinement during the medieval period in Europe significantly contributed to advancements in astronomical knowledge and practice. An astrolabe can be described as a two-dimensional model of the celestial sphere. It consists of several key components: the matter, the main body, the tympan, a plate engraved with coordinate lines for a specific latitude, the rete, a rotating star map, and the alidade, a ruler used for sighting objects. By aligning the rete with the positions of stars, astronomers could simulate the apparent motion of celestial objects and make various astronomical calculations. The significance of astrolabe in medieval astronomy cannot be overstated. It served as both an educational tool and a practical instrument for astronomers. Medieval scholars used astrolabes to teach and learn about the movements of stars, the sun, and the planets. This hands-on approach allowed them to visualize complex astronomical concepts and gain a deeper understanding of the cosmos. The development of astrolabes in Europe was influenced by earlier design from ancient Greece and the Islamic world. The earliest known astrolabes date back to the Hellenistic period, around the 2nd century BCE, with contributions from Greek astronomers like Hipparchus and Ptolemy. However, it was during the Islamic Golden Age that astrolabes were significantly refined and improved. Islamic scholars such as Al-Fazari and Al-Zarqali made crucial advancements in the design and use of astrolabes, and their knowledge eventually reached Europe through translations of Arabic texts. In medieval Europe, the process of developing and refining astrolabes involved several stages. Initially, European scholars translated and studied Arabic manuscripts on astrolabes, gaining insights into their construction and application. One of the key figures in this process was Gerard of Cremona, a prolific translator who brought numerous Arabic scientific works to the Latin-speaking world. Once European scholars understood the principles behind astrolabe construction, they began creating their own versions. These medieval European astrolabes often featured intricate designs and high levels of craftsmanship. Metalworking techniques improved, allowing for more durable and precise instruments. The refinement of engraving methods enabled astronomers to create more accurate and detailed star maps on the Reta. The practical uses of astrolabes in medieval Europe were diverse and essential. One of the primary applications was in navigation. Mariners used astrolabes to determine their latitude by measuring the altitude of the sun or a star above the horizon. This information was crucial for long sea voyages, enabling sailors to navigate with greater accuracy and confidence. Astrolabes also played a vital role in timekeeping. By observing the positions of celestial objects, astronomers could calculate the time of day and night. This was particularly important for religious purposes such as determining the times for daily prayers in Islam and setting the date for Easter in Christianity. Monasteries and cathedrals often had resident astronomers who used astrolabes to maintain accurate liturgical calendars. Additionally, astrolabes were used for various astronomical observations and calculations. They could determine the altitude and azimuth of celestial objects, predict the rising and setting times of stars, and even solve complex problems related to spherical trigonometry. This versatility made them indispensable tools for medieval astronomers and scholars. The development of astrolabes in medieval Europe was a pivotal moment in the history of astronomy. These instruments, with their roots in ancient Greece and the Islamic world, were refined and adapted by European scholars to meet their specific needs. The practical applications of astrolabes in navigation, timekeeping, and astronomical observation highlight the significance in medieval society. John of Sacrobosco, also known as Johannes de Sacrobosco or John of Hollywood, was a pivotal figure in medieval European astronomy. His contributions to the field during the 13th century left an enduring legacy that continued to influence astronomical thought for centuries. Born around 1195, likely in Hollywood, England, Sacrobosco pursued a career as a mathematician, astronomer, and educator, eventually becoming a master at the University of Paris, one of the leading intellectual centers of the medieval world. One of Sacrobosco's most significant contributions to astronomy was his seminal work, De Sphera Mundi. Written around 1230, this concise yet comprehensive treatise on the Ptolemaic cosmological model became a cornerstone of medieval astronomical education. De Sphera Mundi provided a clear and accessible explanation of the geocentric model, which stated that the Earth was at the center of the universe with the Sun, Moon, planets, and stars orbiting around it in perfect spheres. Sacrobosco's De Sphera Mundi was remarkable for its clarity and didactic approach. It was divided into 4 parts, each addressing a specific aspect of Ptolemaic system. The first part described the shape and dimensions of the Earth, affirming its sphericity. The second part focused on the celestial spheres and the motion of the heavenly bodies. The third part explained the phenomena of solar and lunar eclipses, while the fourth part discussed the rising and setting of stars and planets. This structured presentation made complex astronomical concepts more accessible to students and scholars, contributing to the widespread adoption of the Ptolemaic model in medieval Europe. The impact of De Sphera Mundi on medieval astronomy was profound. It became the standard textbook for teaching astronomy in European universities for several centuries. Its influence extended beyond the classroom, as it was translated into multiple languages and widely disseminated. Sacrobosco's work laid the foundation for subsequent astronomical research and education, bridging the gap between the ancient Greek and Roman astronomical knowledge and the emerging scientific developments of the Renaissance. In addition to the Sphera Mundi, John of Sacrobosco made several other notable contributions to mathematics and astronomy. He wrote Algoritmus, a treatise on arithmetic that introduced the Hindu-Arabic numeral systems to European students. This work helped popularize the use of Arabic numerals and the concept of zero, which were essential for advancements in mathematics and science. Sacrobosco also authored a commentary on the Computers, a medieval text used for calculating the date of Easter. In this work, work, he demonstrated his expertise in calendar calculations and his deep understanding of the relationship between astronomical phenomena and timekeeping. This knowledge was crucial for the accurate determination of liturgical dates and the synchronization of religious observances with celestial events. As a teacher at the University of Paris, Sacrobosco's influence extended far beyond his written works. He played a crucial role in shaping the curriculum and training future generations of astronomers and mathematicians. His pedagogical approach emphasized clarity, logical reasoning, and the importance of observational evidence, principles that would later underpin the scientific revolution. Sacrobosco's contribution to astronomy and mathematics were instrumental in preserving and advancing scientific knowledge during the medieval period. His works served as a bridge between the ancient and medieval worlds, ensuring the continuity of astronomical learning. His emphasis on clear and systematic explanations set a standard for scientific writing that continued to inspire scholars long after his time. John of Sacrobosco's contributions to medieval astronomy were monumental. His major work, De Sphera Mundi, provided a clear and accessible explanation of the Ptolemaic system, becoming a cornerstone of astronomical education in medieval Europe. His other contributions to mathematics and calendar calculations further solidified his legacy as a key figure in the history of science. Through his writings and teachings, Sacrobosco influenced generations of scholars and laid the groundwork for astronomical advancements that would follow in the Renaissance and beyond. In addition to John of Sacrobosco, several other European scholars made significant contributions to astronomy during the medieval period. Among these notable figures were Gerard of Cremona and Albertus Magnus, whose work complemented and built upon each other's discoveries, creating a rich tapestry of astronomical knowledge that laid the groundwork for future advancements. Gerard of Cremona was a pivotal figure in the transmission of astronomical knowledge from the Islamic world to medieval Europe. Born in Cremona in Italy around 1114, Gerard was driven by a passion for learning and an eagerness to access the vast body of knowledge preserved by Islamic scholars. To this end, he traveled to Toledo in Spain, which was then a thriving center of intellectual exchange between Christian and Muslim scholars. In Toledo, Gerard immersed himself in the study of Arabic and dedicated himself to translating scientific texts from Arabic into Latin. One of Gerard's most significant achievements was his translation of Ptolemy's Almagest, a comprehensive treatise on the geocentric model of the universe. This work, originally written in Greek, had been preserved and expanded upon by Islamic astronomers. Gerard's translation made the Almagest accessible to European scholars, providing them with a detailed and systematic account of the motions of celestial bodies. His translation was instrumental in disseminating the Ptolemaic model throughout medieval Europe and became a cornerstone of astronomical education. In addition to the Almagest, Gerard translated numerous other astronomical and mathematical works, including texts by Al-Khwarizmi and Al-Battani. These translations enriched the European intellectual landscape and provided the foundation for further developments in astronomy. Gerard's meticulous work bridged the gap between the Islamic Golden Age and the scientific revival in the medieval Europe. Albertus Magnus, also known as Saint Albert the Great, was another towering figure in medieval European scholarship. Born around 1200 in Swabia, Germany, Albertus was a Dominican friar, philosopher, theologian, and scientist. He was known for his encyclopedic knowledge and his efforts to reconcile Aristotelian philosophy with Christian theology. Albertus's contributions to astronomy were part of his broader quest to integrate empirical observation with philosophical inquiry. Albertus Magnus made significant strides in the study of natural sciences, including astronomy. He was a proponent of the observational method and emphasized the importance of direct observation of celestial phenomena. His works included detailed descriptions of the movements of celestial bodies, the phases of the moon, and the nature of eclipses. Albertus was also one of the first medieval scholars to challenge certain aspects of the Ptolemaic system, advocating for a more nuanced understanding of celestial mechanics. Albertus's influence extended beyond his writings. As a teacher at the University of Paris and later at the University of Cologne, he mentored a generation of scholars, including the renowned philosopher and theologian Thomas Aquinas. Albertus's emphasis on empirical observation and his integration of scientific and philosophical inquiry helped shape the intellectual climate of medieval Europe, paving the way for scientific advancement of the Renaissance. The contributions of Gerard of Cremona and Albertus Magnus were complementary and mutually reinforcing. Gerard's translation provided European scholars with access to a wealth of astronomical knowledge from the Islamic world, including the Ptolemaic system and the works of pioneering Islamic astronomers. This influx of knowledge created a fertile ground for intellectual growth and innovation. Albertus Magnus, building on this foundation, emphasized the importance of empirical observation and sought to integrate the newly acquired astronomical knowledge with philosophical and theological principles. His efforts to challenge and refine existing astronomical models contributed to a more sophisticated understanding of celestial mechanics. Together, Gerard of Cremona and Albertus Magnus exemplified the collaborative nature of medieval scholarship. Their work, along with the other notable scholars, created a rich and interconnected web of knowledge that spanned cultures and centuries. This intellectual legacy not only preserved the astronomical achievements of ancient and Islamic scholars, but also fostered the conditions for the scientific revolution that would transform our understanding of the cosmos. The contributions of Gerard of Cremona and Albertus Magnus to medieval astronomy were profound and far-reaching. Gerard's translation of key astronomical texts from the Islamic world enriched the European intellectual landscape, while Albertus's emphasis on empirical observation and philosophical inquiry advanced the study of celestial phenomena. Together, their work complemented and built upon each other's discoveries, laying the groundwork for astronomical advancements that would follow in the Renaissance and beyond. Their legacy serves as a testament to the power of intellectual collaboration and the enduring quest for knowledge. Medieval astronomers faced a multitude of challenges and controversies as they sought to advance their understanding of the cosmos. These obstacles ranged from limited resources and access to texts to opposition from religious authorities and societal constraints. Despite these hurdles, medieval scholars persevered, contributing significantly to the field of astronomy and laying the groundwork for future scientific advancements. One of the primary challenges faced by medieval astronomers was the scarcity of resources and access to knowledge. The fall of the Western Roman Empire in the 5th century led to a period of political and social instability in Europe. Many ancient texts, including astronomical works, were lost or scattered. Monastic schools and later universities played a crucial role in preserving and copying these texts, but the process was slow and labor-intensive. The availability of astronomical instruments such as astrolabes and armillary spheres was also limited, making it difficult for scholars to conduct precise observations and measurements. In addition to these resource constraints, medieval astronomers often faced opposition from religious authorities. The dominant religious institutions of the time, including the Catholic Church, held significant influence over intellectual pursuits. While the Church was not inherently opposed to the study of astronomy, certain aspects of astronomical inquiry were viewed with suspicion. Scholars who proposed ideas that seemed to contradict religious doctrine risked being censored or punished. This tension was evident in the debates over the geocentric versus heliocentric models of the universe. One of the most notable controversies in medieval astronomy was the conflict between the Ptolemaic geocentric model and early heliocentric ideas. The Ptolemaic system, which placed the Earth at the center of the universe with celestial bodies orbiting in perfect circles, was widely accepted by both scholars and religious authorities. However, some astronomers began to question this model, proposing alternative explanations for the observed motions of celestial bodies. For example, the 14th century scholar Nicholas Oresme suggested that the apparent daily motion of the stars could be explained by the Earth's rotation rather than the movement of the entire celestial sphere. Although Oresme ultimately upheld the geocentric model, his ideas hinted at the possibility of a heliocentric system. Controversies also arose from differing interpretations of astronomical phenomena. For instance, the occurrence of comets and eclipses often sparked heated debates among medieval scholars. Some viewed these events as omens or divine messages, while others sought to understand them through natural explanations. Albertus Magnus, for example, challenged the prevailing belief that comets were atmospheric phenomena, arguing instead that they were celestial objects with predictable paths. His ideas were controversial at the time, but laid the groundwork for a more scientific understanding of comets. Despite these challenges and controversies, medieval astronomers made remarkable strides in their field. They developed sophisticated instruments, improved observational techniques, and refined existing models of the universe. Their work was often characterized by a spirit of inquiry and willingness to question established ideas even in the face of opposition. The resolution of many controversies in medieval astronomy came through a combination of dialogue, debate, and empirical evidence. Scholars engaged in rigorous discussions, often within the framework of the emerging university system, to test and refine their ideas. Observational evidence played a crucial role in resolving debates, as astronomers sought to reconcile their theories with the motions of celestial objects. The challenges and controversies faced by medieval astronomers were numerous and complex. complex. Limited resources, opposition from religious authorities, and the fragmented nature of knowledge dissemination all posed significant obstacles. However, through perseverance, collaboration, and a commitment to empirical observation, medieval scholars made lasting contributions to the field of astronomy. Their work laid the foundation for the scientific revolution of the Renaissance, demonstrating the enduring power of intellectual curiosity and resilience in the face of adversity. One of the enduring legacies of medieval astronomy is the preservation and transmission of ancient and Islamic knowledge. The efforts of translators and scholars such as Gerard of Cremona and John of Sacrobosco ensured that crucial astronomical texts and concepts were passed down to the future generations. This preservation of knowledge allowed later astronomers, including Copernicus, Galileo, and Kepler, to build upon the work of their predecessors and make groundbreaking discoveries that revolutionized our understanding of the cosmos. The development of astronomical instruments during the medieval period also had a lasting impact. The astrolabe, for example, evolved into more sophisticated tools used in modern astronomy. The principles behind the astrolabe's design and its applications in navigation and timekeeping laid the foundation for the development of sextants, telescopes, and other advanced instruments. Today's astronomers continue to rely on precise observational tools to study celestial phenomena, reflecting the enduring influence of medieval innovations. Modern advancements in astronomy often draw inspiration from the meticulous observational methods and empirical approach championed by the medieval scholars. The emphasis on empirical evidence, pioneered by figures like Albertus Magnus, remains a cornerstone of scientific inquiry. This methodical approach has led to numerous discoveries, including the identification of exoplanets, the detailed mapping of our galaxy, and the exploration of distant celestial objects using advanced telescopes and space missions. Ongoing research in the history of science also highlights the contribution of medieval astronomers. Scholars continue to uncover and analyze historical texts, shedding light on the intellectual achievements of medieval Europe. This research not only deepens our understanding of the past, but also informs contemporary discussions about the development of scientific thought and the interconnectedness of different cultures and civilizations. Additionally, the legacy of medieval European astronomy is celebrated through various educational initiatives and public outreach programs. Museums, universities, and cultural institutions often showcase the achievements of medieval astronomers, emphasizing their role in shaping the trajectory of scientific progress. By highlighting the historical contexts and contributions of medieval scholars, these initiatives inspire new generations to appreciate the rich heritage of astronomy and pursue their own scientific endeavors. The legacy of medieval European astronomy remains relevant and influential in the modern scientific world. The preservation of knowledge, development of instruments, and empirical approach of medieval scholars continue to inspire and inform contemporary astronomical research. As we explore the cosmos and make new discoveries, we stand on the shoulders of the medieval giants who paved the way for our understanding of the universe. In this episode, we've journeyed through the medieval Europe to uncover the significant contributions of astronomers during this period, highlighting the development of astrolabes and the impactful work of scholars like John of Sacrobosco. We've explored the historical context in which these advancements took place, noting the influence of early astronomical knowledge from ancient civilizations and the Islamic Golden Age, as well as the pivotal role of translations and establishment of monastic schools and universities. We delved into the development of astrolabes, explaining their construction, significance, and practical applications in navigation and timekeeping. This fascinating instrument showcased the ingenuity of medieval astronomers and their ability to refine and enhance the designs they inherited from earlier civilizations. The contributions of John of Sacrobosco, particularly his seminal work De Sphera Mundi, were examined in detail. His clear and systematic explanations of the Ptolemaic system became a cornerstone of medieval astronomical education and influenced generations of scholars. We also highlighted other notable figures like Gerard of Cremona and Albertus Magnus, whose work complemented and built upon each other's discoveries, creating a rich and interconnected web of knowledge. We addressed the challenges and controversies faced by medieval astronomers, including limited resources and opposition from religious authorities. Their perseverance and commitment to empirical observation laid the groundwork for future scientific advancements. Reflecting on modern developments, we noted how the legacy of medieval European astronomy continues to inspire contemporary research and discoveries. The preservation conservation of knowledge, development of instruments, and empirical approach championed by medieval scholars remain foundational to modern astronomy. The importance of medieval European astronomy in the broader history of the field cannot be overstated. The work of these scholars, despite the challenges they faced, laid the foundation for the scientific revolution of the Renaissance and continues to inform and inspire our understanding of the cosmos today. Their legacy serves as a testament to the enduring power of intellectual curiosity and the relentless pursuit of knowledge. Thank you for watching. Keep looking up. Renaissance Europe marked a profound turning point in history, a period when the rigid structures of medieval thought began to crumble under the weight of curiosity and innovation. In this era, art, science, and literature emerged in a triumphant symphony of exploration, setting the stage for a revolution in every sphere of life. The old world, with its strict hierarchies and dogmatic beliefs, was given way to a new age where inquiry and human ingenuity reigned supreme. During this period, Europe became a fertile ground for intellectual growth. Cities like Florence, Venice, and Paris buzzed with lively debates, and scholars, artists, and philosophers gathered in coffee houses and grand halls alike, discussing ideas that challenged the accepted wisdom of their predecessors. The invention of the printing press played a crucial role, disseminating groundbreaking ideas far and wide and allowing the collective mind of society to expand in unprecedented ways. These new ideas questioned long-standing beliefs about the cosmos, the divine, and the natural order of things. This era witnessed a daring shift, a move away from simply accepting inherited knowledge to actively seeking out new explanations through observation, experimentation, and critical thinking. It wasn't just about art or literature. The Renaissance fostered a scientific curiosity that laid the groundwork for modern astronomy. Scholars began to peel back the layers of ancient texts and challenge the geocentric view that had long held sway over European thought. The idea that Earth was the universe's pivot was starting to seem less certain under the modern lens of rational inquiry. In this environment of intellectual liberation, the cosmic order was being reimagined. Renewed faith in human reasoning and empirical evidence made it possible for bold thinkers to propose radical new theories, the very ideas that would later set the stage for transformative astronomical discoveries. As Europe awoke to a world of possibilities, every investigation, every artistic flourish, and every spirited debate contributed to a growing body of knowledge that sought to understand the workings of the universe in all of its complexity. This vibrant awakening created the perfect context for future pioneers in astronomy. It was the fertile soil in which revolutionary figures like Copernicus and Kepler would eventually plant the seeds of new cosmic vision, a vision that would forever change the way humanity perceives its place among the stars. For centuries, the cosmos was viewed through a lens that positioned Earth at the center, a neatly ordered, almost poetic arrangement that appealed to both reason and divine aesthetics. The prevailing geocentric model, inherited from ancient Greek philosophy and later cemented by medieval scholars, portrayed the universe as a series of concentric spheres with Earth at its core. Every star, planet, and celestial body was thought to revolve in perfect circles around our world, a model that resonated with the idea of cosmic perfection. Yet, even as this model held sway, small but nagging inconsistencies began to emerge. Astronomers noted that the graceful paths of the stars did not always conform to the elegant loops and circles that tradition demanded. The puzzling retrograde motion of planets, wherein they appeared to reverse direction for a time, was one such mystery. These observational quirks posed a fundamental challenge. How could a universe designed with divine perfection exhibit such irregularity? This question laid the groundwork for a slow but inevitable paradigm shift. As the Renaissance unfurled its vibrant tapestry across Europe, new tools and techniques in measurement and observation began to take root. Scholars started to rely more on empirical evidence rather than solely on ancient texts or religious dogma. Instruments, though still rudimentary, provided more precise data, and the results began to strain the limits of the geocentric explanation. There was a growing realization that the celestial sphere might not be as perfect as once thought, that perhaps the universe was not a static stage but a dynamic arena governed by natural laws. This awakening prompted scholars to delve deeper into understanding the true nature of planetary motion. The classical idea of perfect circular orbits and aesthetic ideal of the heavens was gradually being replaced by a more complex reality. The growing emphasis on mathematical analysis and systematic observation encouraged astronomers to look beyond tradition. They began to see that the heavens might be governed not by ornate geometries or fixed spheres, but by more elusive and intricate patterns that called for a radical rethinking of cosmic order. This shift was not merely a technical correction, it was a profound transformation in how humanity perceived the universe. The rigid framework of ancient models started to give way to a vision of a cosmos that was both more chaotic and more fascinating than previously imagined. A universe that could be deciphered through careful observation and rational thought, rather than one that rested solely on philosophical and theological dictates. Moreover, this emerging paradigm invited an interdisciplinary approach where mathematics, philosophy, and astronomy converged. Observers began charting planetary motions with renewed diligence, drawing on the power of numbers and geometric reasoning to explain what the naked eye could see. This collaborative spirit between theoretical speculation and practical measurement set the stage for later breakthroughs that would further demystify the cosmos. In essence, this period marked a pivotal moment, when the old, static view of the universe began to crumble under the weight of fresh observations and more inquisitive spirit. The gradual dismantling of the geocentric model birthed a new era in which the cosmos was seen as an ever-changing expanse, a realm of motion and mystery waiting to be understood. This transformative shift in perspective not only redefined our understanding of the heavens, but also laid the crucial intellectual foundation for the revolutionary insights of future astronomers. Amid the vibrant intellectual stirrings of Renaissance Europe, one figure stood poised to reimagine the cosmos in a way that transcended the ancient models: Nicolaus Copernicus. Born into a world governed by tradition and the unwavering certainty of geocentric thought, Copernicus nurtured curiosity that defied the prevailing norms of his time. Rather than clinging to the long-revered notion that the Earth was the immovable center of celestial order, he began to see the universe through a radically different lens. His journey was neither sudden nor facile. It was the product of patience, meticulous research, and the willingness to challenge centuries of established wisdom. In an era where scholarly life was intertwined with the rigid directives of the Church and Aristotelian philosophy, Copernicus's ideas emerged like a quiet yet persistent force. As he immersed himself in the study of mathematics, astronomy, and ancient texts, he encountered hints of earlier heliocentrism, ideas that had flickered in history but never received the clarity they deserved. With careful observation and analytical mindset, Copernicus pieced together astronomical puzzles that had long baffled his predecessors. His revolutionary insight was to reposition the Sun, not the Earth, at the center of the known universe. This audacious idea, detailed in his seminal work De Revolutionibus Orbium Coelestium, was more than a mere adjustment of celestial coordinates. It was a profound paradigm shift. Copernicus proposed that Earth, along with its fellow planets, gracefully orbited the Sun in a harmonious dance. By doing so, he provided a simpler and more unified explanation for the irregularities noted in planetary motion, such as the perplexing retrograde motion that had confounded scholars for generations. His model suggested that what appeared as aberrant movements were in fact the natural consequences of our planet's own shifting position relative to its luminous center. The implications of Copernicus's theory extended far beyond astronomy. By decentering Earth from the cosmic stage, his work questioned humanity's assumed centrality in the universe and invited a more humble yet expansive view of nature's orders. This perspective challenged not only scientific dogmas, but also philosophical and theological constructs that had defined medieval life. As Copernicus meticulously laid out his observations and mathematical calculations, he offered a vision of a universe governed by consistent principles, a vision that would eventually pave the way for later giants like Kepler and Galileo. Throughout his life, Copernicus exhibited a blend of caution and conviction. A dedicated canon at Fromborg Cathedral, he balanced his ecclesiastical duties with virtuosic scholarship, aware that his ideas invited both intrigue and potential ire. His commitment to empirical evidence and rational inquiry carved out a new method of scientific exploration, one that relied on observation and calculation rather than unquestioned tradition. Even as his ideas ignited controversy, particularly among conservative scholars and religious authorities, they gradually ignited debate that would fuel centuries of astronomical advancement. Copernicus's intellectual legacy is woven into the very fabric of modern science. His willingness to challenge the established order not only redefined the movement of heavenly bodies, but also set in motion a chain reaction of discoveries. Through his clear yet bold questioning of old assumptions, Copernicus transformed how humanity would come to understand its place in the cosmos, a transformation that continues to inspire thinkers and explorers alike. The introduction of heliocentric model marked a radical turning point in our understanding of celestial mechanics. As Copernicus's theory began to take shape, the very foundations of astronomical thought were shaken. The heliocentric universe did not merely rearrange the positions of cosmic bodies, it provided an entirely new lens through which to understand the workings of the heavens, offering clarity and simplicity where confusion had reigned for centuries. At the core of his new perspective was a straightforward yet profound observation. The Sun, rather than the Earth, occupied the central stage. This repositioning brought with it a host of explanations and phenomena that had long mystified astronomers. For example, the erratic retrograde motion of planets, the seeming backwards movement observed from Earth, became a natural consequence of our own planet's orbital dance around the Sun. Rather than resorting to complex systems of epicycles and difference to explain these irregularities, the heliocentric model provided an elegant solution that resonated not only with mathematical logic but also with everyday observation. The shift to a sun-centered cosmos invited scholars to re-examine every known detail about planetary motion. By placing the Sun at the centerpiece, astronomers could trace the paths of celestial bodies with newfound simplicity. Every orbit, every shift in brightness, and every apparent collision of orbits across the night sky found a more coherent explanation. This clarity encouraged a move away from relying solely on ancient texts and philosophical traditions towards a dynamic model built on empirical observation and critical analysis. As scholars began to test and validate this model, the heliocentric view quickly emerged from the realm of abstract speculation into the core of scientific discourse. Furthermore, unveiling this new celestial perspective helped break the psychological and intellectual chains that had long tethered humanity to a geocentric narrative. The model not only challenged the scientific ideas of the day, but also the deeply ingrained belief in humankind's centrality in the universe. With the Sun as the axis of our planetary system, a new humility and curiosity were instilled among scholars and the broader public alike. The cosmos ceased to be an orderly stage with Earth as its crown jewel, and became instead a vast, interconnected system where every planet played a part in a grand cosmic ballet. Importantly, the heliocentric universe did not stand in isolation. It created the fertile ground from which later scientific advancements would grow. The model's emphasis on observation and mathematical consistency paved the way for subsequent astronomers. It provided a framework that allowed thinkers like Johannes Kepler to delve deeper into the precise mechanics of orbital motion, ultimately uncovering the elliptical nature of planetary paths and the laws that govern them. This evolutionary step transformed our view of the universe from a static, almost mythic portrait into a dynamic, mathematically governed system of motion. Ultimately, unveiling the heliocentric universe was about more than just revising diagrams in the sky. It represented the triumph of reason, observation, and an unwavering commitment to understanding the natural world. The clarity it brought to the chaotic dance of the heavens challenged all paradigms and inspired generations of thinkers to continue questioning and exploring. With each new observation, the narrative of the cosmos grew richer and more engaging, reflecting a universe that was less a rigid structure of divine perfection and more a vibrant, ever-evolving tapestry of cosmic wonder. The cosmos, as re-envisioned by Copernicus, was a stage primed for further inquiry, but it still held mysteries that beckoned for deeper interpretation. Enter Johannes Kepler, whose genius transformed the hesitant chords of heliocentric model into a full-blown symphony of cosmic harmony. Kepler's work was less about rigid geometry and more about deciphering the natural rhythms of the universe, a pursuit that can be described as listening to the music of the spheres. Kepler inherited a celestial puzzle that had begun to hint at hidden complexities. With the meticulous observations of Tycho Brahe as his guide, Kepler set out to chart the true paths that planets traced as they journeyed around the Sun. The prevailing notion of perfect, circular orbits gradually gave way to a startling realization. The planets moved not in unyielding circles, but in elegant, elongated ellipses. This discovery, encapsulated in his first law of planetary motion, was a pivotal moment. It revealed that the heavens were not governed by an idealized static order, but by a dynamic and measurable harmony. For Kepler, the idea of elliptical orbits was akin to uncovering a cosmic melody that had always been there, hidden behind the illusion of perfection. He proposed that each planet's path is an ellipse, with the Sun at one focus. A concept that not only explained observed phenomena like retrograde motion more simply, but also introduced a new level of mathematical precision to astronomy. His insight was a brilliant blend of observation and intuition, a process that mirrored the rigorous training of a musician attuned to every nuanced note in a complex orchestration. As Kepler delved deeper, he uncovered further layers of cosmic rhythm. His second law, which states that a planet sweeps out equal areas in equal times, provided a glimpse into the inherent flows of celestial movement. This law illustrated how planetary speeds vary. As planets approach the Sun, they move faster. As they drift away, they slow down. This variation wasn't random, it was nature's way of keeping a perfect balance. In essence, Kepler was decoding the time signatures of the universe, revealing that the cosmos obeyed principles of rhythm and balance similar to those found in music. Yet perhaps his most profound contribution was his third law, forged from painstaking calculations that linked the orbital periods of the planets to their distances from the Sun. This harmonic law showed that the square of a planet's orbital period is directly proportional to the cube of its semi-major axis. Such a relationship offered a mathematical elegance to planetary motions that resonated deeply with the ancient idea of cosmic music, a universe where every celestial body played its part in a grand orchestrated performance. Kepler's journey was not just one of scientific discovery, it was a quest to understand nature's secret score. His willingness to let empirical data guide his intuition transformed our understanding of the cosmos. The brilliance of his work laid the groundwork for future luminaries like Newton, who would further unravel the gravitational forces. In the tapestry of scientific revolution, Kepler's legacy is that of a composer who listened carefully to the whispers of the universe, transcribed its hidden harmonies, and encouraged humanity to appreciate the cosmic dance in all its intricate beauty. His laws continue to echo in modern astronomy, a timeless reminder that the universe, much like a symphony, is a masterpiece of order, rhythm, and wonder. Kepler's revelation of his three laws signified more than a series of scientific statements. It was the unveiling of an intricate dance, a cosmic choreography that transformed the way humanity perceived celestial motion. Building on the heliocentric frame introduced by Copernicus, Kepler's law provided the mathematical language to describe how planets truly move and interact in a dynamic universe. Kepler's first law, the elliptical orbit. The first law shattered the long-held belief in perfect circles. Kepler proposed that planets move in ellipses, not circles, with the Sun occupying the center. This elegant adjustment meant that the paths of planets were elongated curves, a departure from the circular orbits that had seemed a divine mandate for centuries. The elliptical shape not only aligned more closely with the detailed astronomical observations, but also infused the cosmos with a realism that the idealized circles simply could not offer. Through his careful analysis of Tycho Brahe's meticulous records, Kepler demonstrated that these elliptical orbits provided a far more precise prediction of planetary positions, a vital clue that the universe was governed not by abstract perfection, but by natural laws accessible to human understanding. Kepler's second law, equal areas in equal times. If the first law set the stage, the second law revealed the rhythm of the celestial dance. According to this principle, a line drawn from a planet to the Sun sweeps out equal areas in equal intervals of time. This law imparts a sense of balance and timing to planetary motion. In practical terms, it means that planets move faster when they are closer to the Sun and slower when they are further away. This speed is not arbitrary. It's a precise mechanism that ensures the conservation of angular momentum. Through this observation, Kepler provided an intuitive understanding of the forces at play, showing that the energy and timing woven into the fabric of space were in perfect harmony with nature's design. Kepler's third law, the harmonious relationship of distances and periods. Perhaps the most mathematically striking of its insights, the third law establishes a clear relationship between the orbital period of a planet and its distance from the Sun. In its simplest form, the square of a planet's orbital period is directly proportional to the cube of the lengths of its semi-major axis. This law created a predictable framework, linking the time a planet takes to orbit the Sun with the size of its orbit. The profound elegance of this relationship is that it applies uniformly across all planets, regardless of their individual characteristics. This discovery not only highlighted the inherent order within the cosmos, but also provided a powerful tool for predicting planetary positions and understanding the structure of our solar system. Together, these laws transformed what had once seemed like an erratic, inexplicable motions into a coherent dance, a fluid interplay of speed, distance, and geometric precision. Kepler's law allowed astronomers to move beyond simple observation. They provided the rigorous mathematical foundation needed to model the motions of planets. In essence, what was once a celestial jigsaw puzzle now emerged as a harmonious symphony that united empirical observation with elegant mathematical truths. This new understanding of planetary motion not only enhanced the predictive capabilities of future astronomers, but also instilled a sense of wonder about the cosmic order. Kepler's meticulous work served as a bridge from the observational insights of the Renaissance to the advanced gravitational theories of Newton and beyond. His laws are a timeless reminder that the universe, with all of its complexity, follows the rules that can be expressed as a graceful dance, a dance that continues to inspire scientists and astronomers alike. In the early decades of the 17th century, Galileo Galilei emerged as a pioneering force with a passion for unraveling the hidden details of the cosmos. Driven by his curiosity and armed with an innovative spirit, Galileo transformed a modest optical instrument into a powerful telescope that would forever alter humanity's window to the heavens. Galileo's enhancements to the telescope allowed him to pierce the veil of the naked eye. When he turned his instrument skyward, the familiar celestial canvas revealed a startlingly different picture. The moon, long thought to be a perfect, unblemished orb, appeared rugged and scarred with mountains, valleys and craters, a dynamic landscape rather than an immutable sphere. This observation not only upended the Aristotelian idea of celestial perfection, but also heralded a transformative period in the scientific approach toward astronomy. Perhaps his most revolutionary discovery came when he observed Jupiter. Instead of a solitary, majestic planet, Galileo found 4 bright objects, later known as the Galilean moons, orbiting around Jupiter. This was a profound demonstration that not all celestial bodies orbited the Earth, providing potent evidence in favor of the heliocentric model advanced by Copernicus and refined by Kepler. His detailed notes and precise sketches captured the motions of these moons, rendering the invisible dynamics of the cosmos accessible to a skeptical audience and challenging the entrenched geocentric view. Yet Galileo's ingenuity did not stop there. His observations of the phases of Venus further undermined the geocentric paradigm by showing that Venus exhibited a full sequence of phases similar to the Moon. This could only be reconciled with the model of a sun-centered system. Additionally, Galileo's study of the Milky Way revealed that what had been perceived as a continuous band of light was actually a dense swarm of innumerable stars. This discovery expanded the known boundaries of the universe and served as a call to re-examine the fabric of the cosmos. Beyond these groundbreaking discoveries, Galileo's methodical approach was as transformative as his observations. He championed rigorous empirical inquiry, meticulously recording data and repeating experiments to ensure reliability. In doing so, he laid down one of the earliest foundations of the modern scientific method. His willingness to challenge established dogma through observation and evidence fundamentally redefined how questions about nature were to be answered. Galileo's telescopic triumph was not merely a leap in technology, it was a bold expedition into the unseen. With each new observation, he invited the world to view the universe not as a static tapestry of divine perfection, but as a vibrant, ever-changing arena of natural phenomena. His work opened the doors for future astronomers and scientists who would continue to peel back the layers of cosmic mystery, cementing his role as a true pioneer of modern astronomy. While Galileo's telescopic revelations lit up the night sky with newfound wonders, they also cast a long, challenging shadow on his personal journey, a journey marked by confrontation, conflict, and a steadfast commitment to the truth. Galileo's discoveries, revolutionary as they were, thrust him into a bitter clash with powerful authorities who clung to traditional geocentric doctrines. As Galileo's findings began to gain traction, they soon came under fire from the religious and political establishments of his day. His insistence that the heavens obeyed empirical evidence rather than rigid interpretation of ancient texts brought him head-to-head with the prevailing forces of the Church. In 1633, Galileo found himself on trial for heresy, a trial that would become one of the most notorious episodes in the history of science. Despite being forced to recant his heliocentric views under pressure, his ideas had already set in motion a shift in human thought that could not be easily reversed. Galileo's struggle was not only a fight for his personal freedom, it was emblematic of a larger battle for intellectual liberation. Faced with the might of institutional dogma, he championed an approach rooted in personal observation, rigorous experimentation, and a willingness to question assumptions. Even under house arrest in the later years of his life, Galileo's writings continue to inspire quiet revolutions among scholars. His works, written with careful reasoning and poetic descriptions of the cosmos, resonated deeply with those seeking a more truthful connection with nature. The implications of Galileo's defiance extended far beyond his own lifetime. His trial and subsequent silence did little to stifle his legacy. Instead, they transformed him into a symbol of intellectual courage, a reminder that the pursuit of knowledge often requires a personal sacrifice. His experiences galvanized future generations of scientists who summoned the strength of empirical evidence and the methods he had helped refine would eventually break free from the chains of dogmatic constraints. Galileo's influence is palpable even today. Modern astronomy, physics, and the broader scientific community owe a great debt to his relentless questioning and his commitment to uncovering the truth. His life story, a thrilling mix of triumphs, trials, and unwavering dedication, continues to inspire not only scientists, but anyone who dares to look beyond what is immediately visible, to question the status quo, and to seek a deeper understanding of the universe. Galileo's battle for truth remains an enduring legacy. His courage to confront established norms in pursuit of natural laws has become a rallying cry for free inquiry, reminding us that sometimes the most profound breakthroughs come at a personal cost. His life and work continue to light a path of discovery, encouraging us to look, to question, and ultimately to embrace the transformative power of genuine observation. The transformative ideas of Renaissance astronomers ignited a revolution that forever changed the humanity's view of the cosmos. The groundbreaking work of Copernicus and Kepler not only redefined celestial mechanics but also reshaped our collective understanding of our place in the universe. Their contributions continue to ripple through time, inspiring generations of thinkers and explorers and laying the intellectual groundwork from which modern astronomy emerged. Copernicus's bold assertion that the Sun, not the Earth, laid at the center of cosmic system challenged centuries of established thought. His heliocentric model was the spark that lit the fire of inquiry during a period when questioning tradition was a daring act. This model did more than rearrange planetary positions. It signified a seismic shift toward empirical investigation and reasoned debate. It urged humanity to discard comforting certainties for a more complex yet profoundly realistic portrayal of the universe. By questioning the status quo, Copernicus instilled an enduring lesson. The pursuit of truth is best served by challenging established paradigms when evidence calls for it. Building on this audacious foundation, Johannes Kepler transformed the abstract idea of a sun-centered universe into a dynamic, mathematically coherent system. His insightful observations revealed that the orbits of planets were not perfect circles, but elegant ellipses, each expressing a harmonious balance between motion and distance. Kepler's three laws of planetary motion provided a tangible framework that explained previously puzzling phenomena, such as retrograde motion, by tying observed behavior to the geometry of the heavens. By doing so, he not only validated Copernican theory through rigorous analysis, but also improved it with a predictive power that was entirely novel in astronomy. The combined legacy of Copernicus and Kepler ignited further breakthroughs in scientific thought. Their willingness to innovate beyond conventional boundaries paved the way for later pioneers like Galileo Galilei, who used new instruments, most notably the telescope, to gather additional evidence in support of the heliocentric model. Even Sir Isaac Newton, whose laws of gravitational force united terrestrial mechanics with celestial motion, built upon the empirical and mathematical foundations established during the Renaissance. This intellectual continuum illustrates how the evolving understanding of the heavens was the result of a collaborative journey, a finding nurtured by successive minds, each expanding upon the revelations of those who came before. Beyond the realm of science, the legacy of the Renaissance Revolution influenced philosophy, culture, and the very way human beings relate to the universe. The heliocentric model diminished the notion of human centrality, encouraging a humbler and more inquisitive perspective. It opened our eyes to the grandeur of a cosmos governed by natural laws instead of a divine whim, thus sowing the seeds for modern secular scientific inquiry. The shift in perspective from a universe centered around humanity to one where Earth is one of many celestial players continues to influence contemporary discussion at the intersection of science and philosophy. Today, our modern telescopes, space probes, and astronomical observatories all echo with the principles first articulated over 500 years ago. As we chart distant galaxies or study the intricate dance of exoplanets, we are reminded that our understanding of the cosmos rests on the shoulders of Renaissance giants. Their resolve to pursue observation, embrace mathematics, and challenge dogmatic boundaries has given us powerful tools to explore the universe. The legacy of the Renaissance Revolution is not merely measured in scientific laws and astronomical models. It is an enduring call to curiosity and courage. It inspires us to keep probing the unknown, to refine our theories, and above all, to remain open to new vistas of discovery. A legacy that even today lights our path to the stars. The journey through the Renaissance Europe reveals a transformative era when human curiosity broke free from medieval constraints, igniting a revolution in our understanding of the universe. This period was a testament to the power of questioning established norms, a spirit that drove visionaries like Copernicus, Kepler, and Galileo to redefine how we perceive the cosmos. Copernicus dared to uproot the geocentric view that had dominated for centuries, positioning the Sun and not the Earth as the center of our celestial system. His heliocentric model, documented with clarity and conviction, not only simplified complex astronomical patterns, but also set in motion a cascade of inquiry that challenged the doctrines of his time. This bold reimagining laid the foundation for a new era, one in which empirical evidence and mathematical reasoning became the tools for unlocking cosmic mysteries. Building upon Copernicus's groundbreaking ideas, Johannes Kepler transformed the conceptual framework of the heliocentric model into a dynamic, measurable system. By revealing that planetary orbits are elliptical and governed by precise laws, Kepler not only resolved long-standing anomalies, but also showcased the inherent harmony of the universe. His laws bridged the gap between raw observation and mathematical elegance, ultimately providing a blueprint that would inspire future discoveries. Galileo's telescopic adventures then expanded the horizons of the cosmic narrative. With his innovative instrument, he unveiled previously unseen details and the multitude of stars in the Milky Way. Galileo's relentless pursuit of truth, despite the fierce opposition he faced, demonstrated the essential role of technology in advancing scientific thought and cemented the importance of empirical inquiry. Today, the legacy of the Renaissance pioneers continues to illuminate our path. Their combined efforts serve as a stirring reminder that the quest for knowledge is an ever-evolving journey, a dance between observation, mathematics, and boundless imagination. In embracing this legacy, we not only honor the trailblazers of the past, but also empower ourselves to challenge the unknown, continually pushing the frontiers of discovery in our cosmic dance. Long before the advent of modern telescopes and space probes, ancient Mesoamerican cultures wove an intricate relationship with the cosmos that was as practical as it was spiritual. In these vibrant civilizations, the sky was not just an abstract expanse, it was a dynamic canvas that influenced every aspect of life, from agricultural cycles and seasonal festivities to mythology and royal authority. The people of Mesoamerica developed an extraordinary astronomical tradition that intertwined precise observation with deep cosmological meaning, revealing a universe where science and spirituality echoed in unison. In the bustling heart of civilizations like the Maya, Aztec, and Zapotec, the night sky was a living record. Observers meticulously tracked the movement of celestial bodies, deciphering patterns in the rising and setting of stars and planets. This engagement wasn't a solitary pastime. It was communal, with astronomers and priests collaborating to create sophisticated calendars and almanacs that guided daily life and marked the passage of time. Celestial events such as the solstices and equinoxes became signals for beginning planting cycles or conducting vital rites, infusing the rhythms of nature with divine significance. The Mesoamerican approach to astronomy was unique in its synthesis of art, science, and ritual. Their observations led to creation of inspiring structures such as observatories and pyramids aligned with precise astronomical bodies. These architectural marvels not only served as religious centers but also as instruments for measuring time and celestial cycles. In each carefully designed edifice, from the towering temples of the Maya to the expansive plazas of the Aztec, the heavens were mirrored on Earth, creating a dialogue between the physical and the divine. Moreover, the cosmology of Mesoamerica was expressed through stories and symbols that showcase the interplay of darkness and light, chaos and order. The constellations, the phases of the moon, and the cycles of Venus were not merely observed, they were celebrated as elements that shaped the destiny of nations. This profound connection to the cosmos established a legacy where the stars were both a source of practical wisdom and a mirror to the human spirit. At the heart of Mesoamerican astronomical tradition stand the Maya, an ancient people whose sophisticated approach to celestial observation continues to astound modern scholars. Mayan astronomers dedicated themselves to recording the rhythmic dance of the heavens with an accuracy that remains unparalleled in the ancient world. Their dedication to understanding celestial cycles was not only rooted in practical applications such as agriculture and ritual timing, but also in a deep cosmological philosophy that saw the universe as a living, interconnected whole. The Maya developed a remarkable observational system that focused on the regularity of celestial phenomena. They meticulously tracked the motions of the Sun, Moon, and key planets, most notably Venus. The cycles of Venus, with its predictable appearances as both morning and evening star, were of special ritual significance. Rather than viewing these movements as mere curiosities, Maya scholars saw them as omens and guides for agricultural and ceremonial events. The precision of their observations is best exemplified by surviving codices such as the Dresden Codex, which contains tables and calculations predicting solar and lunar eclipses as well as planetary cycles. Mayan observatories, often constructed atop pyramids or within specially dedicated structures, were strategically aligned with the rising and setting points of these celestial bodies. Sites like Uxmal and Tikal feature architectural elements that highlight solstices and equinoxes, reinforcing the idea that the Maya not only observed the stars, but integrated their findings into the very fabric of their urban and ceremonial landscapes. These structures served as an open-air laboratories where sky and stone merged to provide a visual calendar of the cosmos. Every line, notch, and alignment was imbued with meaning, turning the act of astronomical observation into an art form that conveyed both scientific insight and spiritual symbolism. The Maya's approach to the cosmos was holistic. Observations were recorded on various media, codices, stelae, and murals, transforming empirical data into a narrative that explained the cosmic order. This narrative was interwoven with mythology and religion, giving rise to stories that explained natural phenomena and reinforced social cohesion. The careful documentation of astronomical events ensured that the cycle of time was not lost. Instead, it was celebrated in intricate cycles that dictated everything from ritual events to agricultural planting, reflecting an extraordinary integration of mathematics, art, and spirituality. Furthermore, the Maya employed a system of sophisticated calendrical calculations that, while typically explored in subsequent sections, were based on their natural unparalleled observational prowess. Their ability to predict eclipses and shadow the movements of Venus with remarkable precision is a lasting testament to their scientific accomplishments. In essence, the Maya's legacy in celestial observation is one of relentless curiosity and innovative thinking. Their efforts laid a remarkable foundation for understanding the cosmos, a foundation that continues to inspire modern astronomy. By blending empirical observation with cultural and spiritual interpretation, the Maya set a high standard for ancient scientific inquiry, reminding us that the quest to understand the universe is as ancient as civilization itself. Mesoamerican cultures, especially the Maya, crafted calendrical systems of astonishing complexity that integrated astronomical observations, mathematics, and ritual significance. At the heart of this calendrical genius lie three interdependent systems: the Tzolk'in, the Hub, and the Long Count, each serving distinct yet interconnected roles in measuring time and weaving cosmology into everyday life. The Tzolk'in, a sacred 260-day cycle, holds a revered position among the Maya. Unlike the solar year, this cycle consists of 20-day names and 13 numbers, repeating in continuous interlocking pattern that yields 260 unique combinations. The Tzolk'in was not only a means of counting days but also a vessel for spiritual and ritual meaning. Each day was believed to possess a distinct character or energy, influencing human affairs, agricultural practices, and ceremonial events. Mayan priests, who were well versed in the sacred calendar, would interpret these day names and numbers to provide guidance on everything from auspicious dates for planting crops to timing important religious ceremonies, thereby aligning community life with cosmic rhythms. In parallel, the Hab provides a civil calendar approximating the solar year, consisting of 365 days. This calendar is divided into 18 months of 20 days each, complemented by a short period of 5 additional days known as the Wayeb. The Hab enabled the Maya and other Mesoamerican people to track the seasons, vital for agrarian societies dependent on precise timing for planting and harvesting. While the Hab may seem purely pragmatic, it also integrated aspects of religious observance. The extra 5 days, although seen as a time of vulnerability or liminality, were charged with symbolic weight, representing transitions and interludes that could invite spiritual reflection or ceremonies to ensure cosmic harmony. The long count takes calendrical precision to an entirely new level, providing a linear count of days that unlock the ability to record historical events across centuries and even millennia. Designed to mark vast epochs, the long count uses vigesimal system, with a modified structure that includes a cycle of 18 in one of its positions, reflecting the solar year's approximation within a larger framework. This system allowed the Maya to chronicle their history with remarkable accuracy. Monumental inscriptions on stelae and in codices detail the beginnings of cosmic cycles, royal succession, and significant astronomical events. The long count's ability to pinpoint dates in a continuous sequence not only underscored the Maya's sophisticated understanding, but also served as a testament to their belief in the cyclical nature of existence, a cosmos in eternal renewal. Together, these three calendrical systems illustrate a holistic view of time, one that fuses empirical observation with ritual practice and mythic storytelling. They provided structured cycles that regulated life on many levels. The Tolkien infused daily existence with divine nuance, the Hab synchronized human activity with the changing seasons, and the long count preserved a historical memory that linked the present to a mythic past and a prophesized future. In essence, the artistry and ingenuity of these calendars reveal not only an advanced scientific understanding of celestial patterns, but also a worldview in which time itself was a living, sacred manifestation of the cosmos. Mesoamerican cultures integrated their profound astronomical knowledge into every facet of life, and nowhere is this synthesis more evident than in their monumental architecture. Across the sprawling cities of ancient Mesoamerica, temples, pyramids, and observatories were built not merely for ritual or habitation, but as precise instruments to mark and interpret celestial events. These structures reveal a culture that saw the heavens and the earth as deeply interconnected, a relationship that could be observed, measured, and celebrated through architectural alignment. Many of the most iconic sites such as Chichen Itza, Uxmal, and Teotihuacan were designed with the movements of the sun, moon, and planets in mind. The ancient architects crafted these buildings so that on key dates, the interplay between light and shadow would create displays of events that the people considered sacred. For instance, at Chichen Itza, the famous El Castillo pyramid is renowned for its serpent shadow phenomenon. During the equinoxes, the setting sun cast a series of triangular patterns along the pyramid staircase, giving the illusion of snake descending the structure. The striking alignment was not an accident. It was a deliberate choice intended to harmonize the built environment with the cyclical patterns of nature. Architectural alignments served multiple purposes. On one level, they provided practical cues to track time and seasonal changes. The precise orientation of these structures allowed priests and astronomers to predict solstices, equinoxes, lunar standstills, and the appearances of key planets like Venus. Such knowledge was essential for agricultural planning, dictating the timing of planting and harvesting cycles. On another level, these alignments carried profound spiritual significance. The connection between the cosmos and the terrestrial realm was embodied in every temple and observatory, symbolizing the belief that human destiny was intertwined with the divine order of the universe. The design of these architectural marvels reflects a deep understanding of geometry and astronomy. Observatories, often situated atop pyramids, were built to offer an unobstructed view of the horizon and the heavens above. Alignments were achieved through meticulous planning and observation, with careful measurements of solar azimuths and the paths of celestial bodies. The resulting structures are not only testaments to the engineering prowess of their creators, but also serve as colossal astronomical instruments. They allowed the ancient Mesoamericans to capture and recreate the motions of the skies, integrating these dynamic elements into static yet living monuments. This merging of sky and earth through architecture was more than functional. It was a form of storytelling. Each structure communicated the culture's cosmological narratives, the cycles of time, the interplay of chaos and order, and the eternal dialogue between humanity and the divine. The alignments embodied the core belief that the cosmos was cyclical and that the patterns observed in the heavens were echoed in the events on Earth. In exploring these architectural alignments, we witness a legacy of collaboration between art, science, and spirituality. The ancient builders transformed stone and space into an open-air calendar and a symbolic bridge between the human and the divine. Their achievements remind us that even without modern technology, the pursuit of celestial wisdom can lead to creations of profound beauty and insight, a testament to the enduring human quest to merge the realms of sky and earth. Astronomy for the ancient Mesoamericans was not solely a science of observation and measurement. It was deeply interwoven with ritual, mythology, and the very fabric of spiritual life. Celestial events were seen as divine signals, carrying both practical guidance for daily living and profound symbolic meaning connecting the human realm to the immortal cosmos. Every observed movement of the heavens was embraced as part of a cosmic narrative. The cycles of the Sun, Moon, and Venus were not merely astronomical phenomena but powerful omens and allegories imbued with the essence of life, death, and regeneration. For instance, the predictable phases of Venus offered more than just a temporal marker. They were intimately linked to the mythic cycles of creation and renewal. This celestial body was often associated with deities who held sway over fertility, prosperity, and the balance between light and darkness. Such associations led to elaborate ceremonies designed to honor these gods, whose blessings were thought indispensable for the continuation of agricultural cycles and the well-being of society. Rituals in Mesoamerican cultures were carefully timed to align with specific astronomical events. The alignment of temples with solstices and equinoxes, for example, was not only a feat of architectural precision, but also a purposeful act of invoking cosmic power. Ceremonial centers such as those at Chichen Itza and Teotihuacan showcased this dual purpose, serving as observatories during the day and sacred spaces for nighttime rites. During significant celestial events like eclipses or the appearance of particular constellations, rituals ranged from communal dances and fasting to offerings and blood sacrifices, all performed with the intention of appeasing the gods and ensuring cosmic harmony. Ancient myths provided the framework for understanding these experiences. Stories passed down through generations recounted the struggles and triumphs of powerful deities whose actions orchestrated the cosmos. The Popol Vuh, a foundational myth of the Quiche Maya, entwined the origins of humanity with celestial events, casting the stars as both witnesses and participants in the eternal cycles of creation and destruction. Such narratives reinforce the belief that the cosmos was a dynamic entity, eternally in motion and full of purpose, where every star and every shift in the sky carried an echo of divine intent. In ceremonies, the roles of astronomer priests were paramount. They were both the custodians of astronomical knowledge and the interpreters of celestial omens. Their observations informed the timing of sacrificial rites and communal festivities, ensuring that every ritual was in synchrony with the cosmic calendar. This delicate balance between observation and belief fostered a culture where science and spirituality were two sides of the same coin, a unity that celebrated the mystery of existence while seeking to understand it through methodical observation. The spiritual dimension of Mesoamerican astronomy reminds us that the quest for knowledge can be as much about nurturing the soul as it is about worldly advancement. The intertwining of myth, ritual, and cosmic order serve not only to ground the community in a shared sense of destiny, but also to elevate their understanding of the universe to a realm of sacred wisdom. In honoring the celestial rhythms through ritual, the ancient Mesoamericans created a legacy where the dance of the stars was celebrated as a divine conversation, one that continues to inspire modern seekers to explore the eternal dialogue between humanity and the cosmos. The astronomical wisdom of ancient Mesoamerica continues to loom large even in contemporary discussions about the cosmos. By blending precise observation, intricate calendar systems, and a deep well of spiritual meaning, Mesoamerican people created a legacy that challenges modern perceptions and encourages us to see science and art as fundamentally intertwined. Their practices remind us that the interpretation of celestial phenomena goes far beyond pure measurement. It is a vibrant narrative that connects humanity to the universe in profound, often unexpected ways. One of the most striking aspects of this legacy is how the ancient Mesoamericans harnessed careful observation as both a scientific tool and an artistic inspiration. Long before modern instruments, they developed observatories and erected monumental structures aligned with the movements of the heavens. Their dedication to tracking solar cycles, lunar phases, and the paths of planets resulted in remarkably accurate records of celestial events. This precision was not only a practical asset for agriculture and ritual timing, but also a testament to the human drive to understand and celebrate the natural world. Modern audiences equipped with advanced technology can still learn from the disciplined curiosity these ancient astronomers exhibited. The complex calendrical systems of the Maya and other Mesoamerican cultures such as the Tzolk'in, Hab, and the Long Count also remain a source of fascination today. These calendars encapsulated a holistic view of time, interweaving cyclical patterns with cosmic events and serving as a bridge between the earthly and the divine. They revealed that time, as experienced by these cultures, was far more than linear progression. It was an ever-renewing cycle filled with ritual, myth, and natural wonder. This approach challenges the modern tendency to segregate scientific calculation from artistic interpretation, encouraging us instead to view temporal cycles as narratives that imbue our world with meaning. Additionally, the integration of spiritual practices with astronomical observations created symbiotic relationship between science and the sacred. Celestial events were not only measured and predicted, they were celebrated, ritualized, and thought to carry messages from the gods. This mindset fostered a way of engaging with the cosmos that was vibrant and full of reverence. For modern cosmologists and enthusiasts, the Mesoamerican view of the sky offers a robust reminder that scientific inquiry need not sacrifice beauty, mystery, or emotional impact. Instead, it can be enriched by an artistic and philosophical perspective that honors the awe-inspiring scale of the universe. In today's era of space exploration and digital technology, the starry legacy of Mesoamerica continues to inspire curiosity and wonder. It invites us to look at our modern instruments and theories not as replacements for ancient wisdom, but as an extension of age-old quest to understand our place in the cosmos. The enduring lessons from the starry past show us that science and art are not separate, but complementary forces that together empower us to see the universe in all its multifaceted grandeur. By embracing this integrated approach, we can open new avenues of inquiry while remaining connected to the rich cultural heritage that has long celebrated the dance of the stars. The ancient Mesoamerican legacy stands as a timeless call to explore, celebrate, and redefine our understanding of the universe, a legacy that continues to light our way in the ever-evolving journey through the space and time. The journey through the astronomical wisdom of ancient Mesoamerica reveals a profound and enduring legacy that continues to resonate in modern thought. From the meticulous observations and sophisticated calendrical systems to the majestic architectural alignments and spirituality-charged rituals, this cultural heritage offers a vibrant tapestry of knowledge that integrates science, art, and mythology. The Mesoamerican approach to the cosmos reminds us that the search for knowledge has always been as much an aesthetic and spiritual endeavor as it has been a practical one. The intricate calendars, Tzolk'in, Hab, and the Long Count, are more than mere timekeepers. They are embodiments of a worldview where time is cyclic, layered and infused with meaning. These systems not only drove agricultural practices and ceremonial activities but also reflected a deep-seated belief in continual renewal of life. This cyclical concept of time challenges the linear perspectives that dominate modern science, inviting us to see history and natural phenomena as interconnected events resonating through eternity. Monumental structures aligned with key celestial events further underscore the Mesoamerican commitment to blending empirical observation with spiritual significance. Their pyramids and observatories stand as a testament to a culture that saw the stars as an open book of divine messages, an ever-unfolding narrative that guided societal rituals and personal destinies. The precise architectural alignments and celestial correlations are enduring symbols of the ancient commitment to harmonizing human life with the natural cycles of the universe. This legacy compels modern audiences to reconsider the division between scientific inquiry and spiritual exploration. In today's era of technological advancement and space exploration, the ancient Mesoamerican approach offers a refreshing perspective, a reminder that the cosmos is not only to be measured and analyzed, but also to be revered and celebrated. Their integrated view of the universe continues to inspire curiosity, reverence, and wonder, encouraging us to look up at the stars with a sense of both analytical rigor and profound awe. The night sky has always been a source of wonder, but for Indigenous Australian cultures, it is so much more than a celestial display. For tens of thousands of years, the stars have guided their lives, shaped their stories, and provided an intricate map of the universe. Their connection to the cosmos isn't just profound, it's among the oldest continuous astronomical traditions on Earth. This knowledge, passed down through generations, is deeply interwoven with their spirituality, culture, and daily life. Indigenous Australians view the sky as a living, dynamic storybook, a reflection of the land below and their place within it. Stars and celestial patterns form the backbone of dreaming stories, which not only explain the origins of the world, but also teach important lessons about community, respect, and the natural order. These stories are not just folklore, they are an integral part of preserving their identity and understanding the universe. But the significance of Indigenous astronomy extends beyond culture. Indigenous Australians use the stars for practical purposes, such as navigating vast distances across deserts and predicting the changing seasons. Their observations of celestial events like eclipses and comets, as well as their tracking of movements of planets, showcase an advanced understanding of the natural world. This episode delves into the brilliance of Indigenous Australian astronomy, uncovering its cultural depth, scientific relevance, and the ways it continues to inspire modern researchers. By exploring this ancient wisdom, we gain not only a richer understanding of the cosmos, but also a greater appreciation for the diverse ways in which humanity connects with the universe. From dreaming stories to groundbreaking scientific insights, the knowledge of Indigenous Australians reminds us of the boundless creativity and curiosity that defined our shared human experience. For Indigenous Australian cultures, the night sky isn't just an expanse of stars. It is the very fabric of existence. Every twinkling light holds meaning, every constellation a story, and every celestial event is woven into a deeper understanding of life, the land, and the universe. This spiritual connection to the cosmos forms the foundation of their dreaming stories, timeless narratives that explain the origins of the world and teach profound lessons about humanity's relationship with nature and each other. Take for instance the Emu in the night sky, a dark constellation formed by the dust lanes of the Milky Way. In many Indigenous traditions, this celestial figure is not merely a decoration, but a guide for life. Its appearance in the night sky signals the start of the emu breeding season, a vital time for communities living off the land. Through stories like these, Indigenous Australians demonstrate how the sky mirrors the rhythms of the life on Earth. Dreaming stories also offer insights into morality and social cohesion. Constellations are often seen as ancestral spirits watching over their descendants, reminding them of their responsibilities to the land and their community. The Pleiades, or Seven Sisters, feature prominently in many dreaming tales, often symbolizing family bonds, loyalty, and resilience. These stories are not static. They evolve and adapt, yet their core messages remain deeply rooted in values of respect and connection. Importantly, the sky isn't just a canvas for spiritual meaning, it is also a tool for preservation. Dreaming stories tied to the stars act as a mnemonic system for passing down knowledge across generations. Whether it's understanding seasonal changes, navigating vast landscapes, or interpreting celestial events, the stars are central to their way of life. Through these narratives, the cultural and spiritual essence of Indigenous Australian astronomy has endured for tens of thousands of years. From the intricate patterns of constellations to the lessons embedded in dreaming stories, the night sky is a profound source of inspiration and wisdom. It reminds us that astronomy isn't just about telescopes or equations. It is also a deeply human pursuit, one that connects us to the past, the land, and the boundless mysteries above. In Indigenous Australian cultures, the stars are not distant objects to be studied. They are companions, ancestors, and storytellers, eternal guides shining down on life below. For Australian cultures, the night sky was more than a collection of shimmering lights. It was a compass, calendar, and guide intricately mapped to the vast Australian landscape. Long before GPS or even magnetic compasses, these communities mastered celestial navigation, relying on the stars to traverse enormous distances across deserts, forests, and coastlines. This profound understanding of the night sky reflects a knowledge system that's as practical as it is beautiful. The Southern Cross, for example, plays a pivotal role in navigation. Unlike the North Star, which is fixed in the Northern Hemisphere, the Southern Cross offers a more dynamic yet equally reliable guide for orienting oneself. Indigenous Australians would use its position to determine true south and find their way across the land. This constellation's importance transcends its function. It is embedded in dreaming stories and represents cultural and spiritual connection to the earth and sky. Yet, navigation wasn't just about finding direction. It was deeply tied to seasonal changes and survival. Indigenous Australians observed how the stars shifted with seasons and used these changes as cues for movement. When specific constellations appeared or disappeared from view, they knew it was time to move to new areas where food and water would be abundant. For example, the appearance of the Orion constellation signaled the onset of the wet season in the north, prompting communities to prepare for the changing environment. The night sky also provided an enduring map of the land. Certain stars and constellations were associated with specific landmarks, creating a celestial mirror of the terrain below. By following the songlines or dreaming tracks, paths that link the land and sky, travelers could navigate vast distances with remarkable accuracy. These songlines were not just practical routes but carried stories and teachings that connected people to the land and their ancestors. Every step was guided by a verse, every landmark tied to a star, and every destination enriched by cultural meaning. One of the most extraordinary aspects of Indigenous navigation is its holistic nature. It isn't just about looking at the stars in isolation, but understanding their connection to the land, the seasons, and the community. This comprehensive approach highlights a harmonious relationship with nature, where knowledge of the sky isn't separate from life on Earth. It's integrated into every facet of it. Modern researchers have marveled at the accuracy of this celestial navigation. Studies have shown that these ancient techniques can rival and in some cases surpass modern tools. Collaborations between indigenous communities and astronomers continue to shed light on how traditional methods can inspire and enhance contemporary understanding of navigation and astronomy. Indigenous Australian knowledge of the stars as tools for navigation is a testament to human ingenuity, patience, and a deep connection to the natural world. It bridges the cosmic with the terrestrial, showing us that the night sky isn't just a backdrop. It's a vital, guiding force that has not only practical insights but also a profound respect for intricate relationship between humanity and the cosmos. To Indigenous Australian cultures, the sky is not just a static spectacle of stars. It is a dynamic and ever-changing narrative. Celestial events like eclipses, comets, or the phases of the moon hold significance far beyond their scientific explanations. They are deeply connected to cultural beliefs, practical applications, and an intrinsic understanding of the universe. Indigenous Australians interpreted these phenomena with remarkable insight, weaving them into their stories and using them as tools to navigate life. Take lunar phases, for instance. Indigenous Australians observed how the cycle of the moon influenced tides, animal behavior, and even human activity. Communities along the coastline, such as those in northern Australia, use the moon's phases to predict optimal fishing times or to anticipate changes in sea levels. These observations were practical, but they were also tied to cultural practices. The waxing and waning moon often symbolized life cycles, growth and renewal, creating a spiritual connection between the celestial body and daily existence. Eclipses, on the other hand, carried more complex interpretations. While modern astronomy explains them as celestial alignments of the Sun, Moon and Earth, Indigenous Australians view them as rare and significant occurrences. Some traditions described eclipses as moments of cosmic harmony or reconciliation, while others saw them as warnings or omens tied to community life. Regardless of the interpretation, eclipses were treated with reverence and sparked conversations about the mysteries of the universe. Comets were equally fascinating. Indigenous Australians noted their unpredictable appearances and often saw them as messengers of change. Some cultures associated comets with significant events such as the arrival of visitors or shifts in weather patterns. In contrast to the fleeting nature of comets, constellations and planets were observed over longer periods, allowing communities to track their movements and integrate this knowledge into their understanding of time and space. The seasonal changes in the night sky also informed agriculture, hunting, and resource management. For example, the rising of certain stars or constellations marked the transition into different seasons. The appearance of the star cluster Orion coincided with the wet season in the north, signaling the time to prepare for floods and harvest water-based resources. Such celestial markers served as reliable indicators of environmental shifts, enabling communities to plan their activities with precision. Indigenous Australians didn't just observe celestial events, they interpreted them in ways that were both scientific and philosophical. Their explanations bridged the gap between empirical observation and spiritual meaning, creating a holistic framework of knowledge. This approach demonstrates a profound understanding of the interconnectedness of the cosmos and life on Earth. Modern astronomy continues to be inspired by these interpretations. Researchers have studied how Indigenous Australians predicted eclipses or tracked planetary movements with surprising accuracy, often finding correlations between traditional practices and contemporary scientific methods. These collaborations highlight the brilliance of Indigenous knowledge systems and their enduring relevance in understanding the universe. By exploring Indigenous interpretations of celestial events, we not only gain insight into the ancient wisdom, but also learn to appreciate the depth of human curiosity and creativity. Their perspective reminds us that the sky is not just something to look at, it's something to live with, to learn from, and to connect to on multiple levels. Indigenous Australian astronomy isn't just steeped in cultural and spiritual significance, it also demonstrates remarkable scientific sophistication. For tens of thousands of years, Indigenous Australians have observed, recorded, and interpreted the movements of celestial objects with precision, blending empirical knowledge with cultural meaning. While some might view their astronomical practices as folklore, many modern researchers have found astonishing correlations between traditional Indigenous knowledge and contemporary scientific understanding. Take, for example, their interpretation of the Southern Cross. Indigenous Australians use this constellation not only for navigation, but also to track its shifting position in the sky throughout the year. Such observations reflect an advanced understanding of the Earth's axial tilt and the changing seasons. Stone arrangements like Wurdi Yowang in Victoria appear to align with summer and winter solstices, showcasing knowledge of celestial mechanics comparable to that of a Stonehenge. This alignment suggests deliberate and systematic observation of the sun's movements over centuries. The scientific relevance of Indigenous astronomy extends to the tracking of planetary movements. Venus, often referred to as the morning star, holds a special place in Indigenous traditions across Australia. By observing its patterns and appearances, Indigenous Australians demonstrated a deep understanding of its orbital behavior. The accuracy of their interpretations rivals that of ancient astronomical systems in other parts of the world, such as the Mayan or Babylonian traditions. Perhaps one of the most impressive aspects of Indigenous Australian astronomy is their ability to predict celestial events. For example, certain communities could anticipate eclipses, recognizing them as recurring phenomena rather than random occurrences. This suggests that Indigenous Australians had a conceptual grasp of the cyclic nature of celestial alignments. Their observations of comets and their connections to changes in weather or environmental conditions show how carefully they monitored the interplay between celestial and terrestrial events. Modern science has also corroborated the long-term observations of Indigenous Australians regarding variable stars. Some traditions describe stars that brighten and dim over time, a phenomenon that aligns with what astronomers now understand as stellar variability. The study of pulsating stars, such as Cepheid variables, underpins modern astrophysics, highlighting the extraordinary depth of Indigenous astronomical knowledge. Collaborations between Indigenous Australians and modern scientists continue to shed light on the scientific relevance of traditional knowledge. For instance, Indigenous elders have shared their understanding of the phases of the moon, contributing insights into ecological cycles and animal behaviors tied to lunar patterns. These partnerships not only validate the accuracy of Indigenous interpretations, but also bridge ancient wisdom and modern methodologies, creating a richer understanding of the cosmos. Through Indigenous Australian astronomy, we see the intersection of science, observation, and cultural meaning. It challenges us to expand our definition of science, recognizing that systematic inquiry can take many forms. Their astronomical knowledge is not a relic of the past, but a living tradition, reminding us that humanity's relationship with the stars transcends borders and eras. The integration of this ancient wisdom into modern science is a powerful testament to the enduring brilliance of Indigenous perspectives. It reveals a timeless truth: the sky connects us all. Indigenous Australian astronomical knowledge is not just a relic of the past. It continues to make waves in modern astronomy, offering fresh perspectives and invaluable insights. For millennia, Indigenous Australians have meticulously observed the stars, planets, and celestial phenomena, and these rich traditions are now gaining recognition for their scientific merit. Today, the collaborations between Indigenous communities and researchers are reshaping how we understand the cosmos, blending ancient wisdom with contemporary science. One of the key contributions lies in Indigenous approaches to mapping the night sky. Many Indigenous star maps focus on dark spaces between stars rather than just the stars themselves. This perspective is unique to the Southern Hemisphere and offers an alternative framework for understanding celestial patterns. For example, the Emu in the night sky, a dark constellation formed by the dust lanes of the Milky Way, is not only a cultural symbol but also a practical tool. Modern astronomers are beginning to appreciate how this approach complements conventional star-based mapping systems, particularly when studying regions like the Milky Way's core. In addition to their unique perspective on celestial patterns, Indigenous Australians have a profound understanding of the long-term changes in the night sky. This knowledge is invaluable in the study of stellar and planetary cycles. For instance, stories describing stars that change in brightness align with modern observations of variable stars, those that dim and brighten over time. These narratives have prompted researchers to re-examine historical oral accounts, finding evidence that complements current astrophysical theories about stellar evolution. Collaborative projects are another arena where Indigenous contributions are shining. Across Australia, Indigenous elders and astronomers are working together to document and preserve traditional star knowledge. Programs like the ARC Centre of Excellence for All-Sky Astrophysics in 3D actively incorporate Indigenous perspectives into their research, ensuring that these ancient understandings continue to inform modern science. Efforts like these are not only enriching academic studies, but also fostering greater respect for Indigenous science as a legitimate and valuable field of study. One striking example of this collaboration is the use of stone arrangements like Wurdi Yuwang in Victoria. These structures, believed to align with the solstices, have sparked new discussions about the astronomical achievements of ancient societies. The precision with which these stones were placed challenges the notion that advanced astronomy was exclusive to civilizations like those of ancient Mesopotamia or Europe. Instead, they highlight the global nature of early astronomical pursuits and the ingenuity of Indigenous Australian communities. Another notable contribution is the growing effort to integrate Indigenous star lore into education and outreach. Indigenous Australian knowledge is increasingly being featured in planetariums, museums, and schools, presenting the sky through a cultural lens that broadens our understanding of humanity's relationship with the cosmos. This approach not only enriches public appreciation of astronomy, but also empowers indigenous communities to reclaim their narrative and share them with a global audience. By recognizing the contributions of Indigenous Australian astronomy, modern science takes a step toward inclusivity and diversity, acknowledging that knowledge comes in many forms. This partnership between ancient wisdom and cutting-edge research is a testament to the timelessness of human curiosity and ingenuity, reminding us that every perspective, no matter how ancient, has a place among the stars. For tens of thousands of years, Indigenous Australian astronomical knowledge thrived, deeply embedded in culture, spirituality, and daily life. The night sky served not only as a guide, but as a profound expression of identity and connection to the land. However, the arrival of European colonists in the late 18th century brought profound and devastating changes, disrupting these time-honored traditions. Colonization caused immeasurable loss to indigenous cultures, including the suppression and marginalization of their astronomical knowledge. One of the most significant impacts of colonization was the displacement of indigenous communities from their ancestral lands. For cultures so deeply tied to the land and the sky, this separation was catastrophic. Sacred sites linked to the celestial events, such as stone arrangements used for solstice observations, were desecrated or destroyed. Without access to these places, the cultural practices and stories connected to them were at risk of being lost forever. The colonial narrative also imposed European systems of knowledge as superior, dismissing indigenous knowledge as primitive or irrelevant. This included their astronomy, which was misunderstood or ignored by early settlers. Indigenous Australians were rarely recognized as scientists or navigators, despite the sophistication of their celestial understanding. The imposition of Western education systems further marginalized traditional knowledge, favoring a Eurocentric view of the cosmos while silencing indigenous perspectives. Despite these challenges, indigenous communities showed remarkable resilience. Knowledge that could not be openly practiced was preserved through oral traditions passed down quietly within families and communities. The continuity of these traditions, even in the face of immense adversity, is a testament to the strength and determination of Indigenous Australians to keep their culture alive. The astronomical knowledge of Indigenous Australian cultures is a testament to human ingenuity, resilience, and creativity. For tens of thousands of years, they have looked to the skies not just for answers, but for guidance, meaning, and inspiration. Their understanding of the cosmos, deeply intertwined with cultural and spiritual beliefs, offers a perspective that enriches our collective appreciation of the universe. Throughout this episode, we've explored how Indigenous Australians interpret the stars as living stories, navigational tools, and markers of celestial events. We've seen how their wisdom rivals and often complements modern scientific methods, from the emu in the night sky to the precise alignment of stone arrangements like Wurdi Yowang. Their contributions to astronomy reveal an intricate relationship between the Earth, the sky, and the people who walk between them. But beyond the science, what stands out is the enduring relevance of their knowledge. Despite the challenges of colonization, Indigenous Australians have preserved these traditions, and today, they are finally being recognized for their significance. By integrating this ancient wisdom into modern astronomy, we are not only validating its accuracy, but also ensuring that it informs our understanding of the cosmos in a more holistic way. As we conclude, let's remember the broader message that this knowledge imparts. The night sky, universal and unchanging, holds lessons for all humanity. It teaches us that we are all connected across cultures, across time, and across the vastness of space. By respecting and celebrating the contributions of Indigenous Australian cultures, we are reminded that science is not separate from humanity. It is deeply rooted in it. Their stories and insights shine as brightly as the stars themselves, guiding us toward a future where knowledge is shared and perspectives are united under one expansive sky. Astronomy has always been humanity's window to the universe. From the earliest stargazers charting the heavens with the naked eye to groundbreaking revelations about our place in the cosmos, it's a story as old as time itself. Yet the astronomy we know today, the modern, tech-savvy, data-driven discipline, has evolved beyond anything our ancestors could have dreamed of. The turning point came with the advent of telescopes. When Galileo first aimed his rudimentary telescope at the night sky in the early 1600s, it marked the beginning of observational astronomy. He saw moons orbiting Jupiter, craters on the moon, and stars invisible to the naked eye. This was just the start of humanity's quest to uncover the secrets of the cosmos. Fast forward to now, and telescopes like the James Webb Space Telescope are delivering images and data so breathtakingly detailed that they've rewritten our understanding of the universe. Modern astronomy is not just about looking up, it's about seeing deeper, further, and more clearly than ever before. But here is what makes modern astronomy truly remarkable. It's no longer limited to a select group of scholars. Now, astronomers are equipped with tools that capture not just visible light, but also radio waves, X-rays, and gamma rays, allowing them to peer into phenomena like black holes, neutron stars, and distant galaxies. Observatories like the Hubble Space Telescope and radio arrays such as the Atacama Large Millimeter Array have opened up entirely new realms of discovery. We are no longer bound by Earth's atmosphere. Space itself has become our observatory. Modern astronomy isn't just about studying the stars though, it's about untangling the narrative of the universe. Every discovery, from exoplanets circling distant suns to the faint echoes of Big Bang, adds a new chapter to this epic tale. And it's not just scientists contributing to this story. Data from these state-of-the-art instruments are shared widely, allowing for collaboration on a global scale. The spirit of discovery that once drew ancient civilizations to study the heavens remains very much alive. Today, astronomy doesn't just answer the age-old question, what's out there? It challenges us to ask even more profound ones. Where did we come from? Are we alone? And ultimately, what is our destiny in this vast and seemingly endless expanse? The journey of modern astronomy has only just begun. If modern astronomy is a window to the universe, technology is the hand that opens it wider. The tools and techniques employed by astronomers today have revolutionized our ability to observe, understand, and even predict cosmic phenomena. From high-tech telescopes to advanced computational methods, technology is the driving force behind the stunning progress we've witnessed in exploring the universe. One of the most profound technological advancements in astronomy has been the development of space-based observatories. Instruments like the Hubble Space Telescope and the James Webb Space Telescope have liberated astronomers from the limitations imposed by Earth's atmosphere. On the ground, air turbulence distorts the light entering telescopes, blurring the images. But in the vacuum of space, these telescopes can capture crystal clear views of distant galaxies, nebulae, and star clusters. For example, the James Webb Space Telescope has delivered breathtaking infrared images that reveal the structure of galaxies billions of light years away, data that would be impossible to gather from Earth. Space technology isn't just a step forward, it's a quantum leap. And let's not forget radio astronomy. Traditional optical telescopes see the universe in visible light, but radio telescopes such as the Atacama Large Millimeter Array enable scientists to detect signals emitted in the radio spectrum. These telescopes can observe phenomena invisible to optical telescopes like the formation of planetary systems or the behavior of molecular clouds that birth stars. By combining radio data with optical and infrared observations, astronomers build a richer, multidimensional picture of the cosmos. Beyond telescopes, technology has given rise to a new era in data processing and simulation. Observations produce mountains of data, far more than any individual scientist could analyze. Enter artificial intelligence and machine learning, which sift through this data to identify patterns and anomalies. Take pulsars for instance, neutron stars that emit regular bursts of radiation. AI-powered algorithms can pinpoint pulsars buried in vast datasets that would take humans years to comb through. Simulations powered by supercomputers also allow astronomers to model the evolution of galaxies or the dynamics of black holes, offering insights that are otherwise inaccessible. Technology doesn't just enhance observations, it empowers exploration. Robotics has played an essential role in sending spacecraft to study our cosmic neighbors, from the Mars rovers examining the red planet's surface to missions like Voyager and New Horizons exploring the outer reaches of the solar system. These technological marvels act as our robotic emissaries, venturing where humans cannot. Instruments on board these spacecraft are engineered with incredible precision, capable of analyzing the chemical composition of soil or detecting microscopic particles in space. The data they send back is not only transformative for planetary science, but also enriches our understanding of Earth's place in the cosmic neighborhood. Networking and collaboration are also vital aspects of technology's impact on astronomy. Projects like the Event Horizon Telescope outline how interconnected systems can achieve extraordinary feats. By linking radio telescopes across the globe into a single network, the EHT captured the first image of a black hole, a moment that made history. Technology facilitates global teamwork, enabling researchers from different countries and disciplines to contribute their expertise. Additionally, technology has helped make astronomy accessible to the public. Smartphone apps can turn everyday stargazers into amateur astronomers, identifying constellations and even tracking the International Space Station's location in real time. Planetarium software and virtual reality experiences bring celestial wonders to life, allowing anyone to explore the surfaces of planets or the depths of distant galaxies. Public access to such tools has fostered a deeper appreciation for astronomy, inspiring the next generation of scientists. However, none of these advancements would be possible without the engineers and innovators behind the scene. People like George Hale, who designed the first giant telescopes, and the teams who developed adaptive optics to counteract atmospheric distortions, are unsung heroes in the story of astronomy's technological evolution. Their work connects with the legacy of visionaries like Galileo and Newton, creating a continuum of progress that links past discoveries with future possibilities. Technology doesn't merely aid astronomy, it transforms it, opening up realms that were once considered unknowable. And as technology continues to advance, so too does our understanding of the universe, proving that the limits of human curiosity are boundless. In this dance between science and innovation, astronomy takes center stage, unveiling secrets of the cosmos one discovery at a time. The role of technology in astronomy isn't just a supporting act, it's the star of the show. Modern astronomy has seen a cascade of groundbreaking discoveries that have fundamentally altered our understanding of the universe. These moments of revelation, born from advances in technology, collaboration, and sheer intellectual ingenuity, are the milestones of ever-evolving cosmic story, a story that continues to amaze and inspire. One of the most transformative breakthroughs in recent years have been the discovery of thousands of exoplanets, or planets outside our solar system. The first confirmed exoplanet detection came in 1992, but it wasn't until missions like the Kepler Space Telescope that astronomers truly began unveiling the diversity of worlds in the cosmos. These discoveries have revealed planets orbiting stars at incredible distances, some even in the star's habitable zone, where liquid water might exist. Perhaps the most exciting discovery in this domain came with TRAPPIST-1, a system hosting 7 Earth-sized planets, 3 of which lie in the habitable zone. Thanks to instruments like the James Webb Space Telescope, we can now study the atmospheres of these distant worlds, searching for signs of life and clues about their composition. Another breakthrough came with the observation of gravitational waves, ripples in space-time first predicted by Albert Einstein over a century ago. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO for short, detected these waves for the first time, generated by the collision of 2 massive black holes. This discovery opened an entirely new way of observing the universe, allowing astronomers to listen to cosmic events rather than merely observing them through electromagnetic signals. Subsequent detections have revealed neutron star mergers, providing insights into the origins of heavy elements like gold and platinum. The study of black holes has also advanced dramatically in modern astronomy. In 2019, the Event Horizon Telescope provided humanity with its first ever image of a black hole, a supermassive black hole at the heart of the galaxy M87. The image showed the glowing ring of material surrounding the black hole's event horizon, offering direct visual evidence of these enigmatic objects. This discovery was the result of a global collaboration of scientists and observatories, showing the power of teamwork in astronomical research. And in 2022, the EHT followed up with an image of Sagittarius A star, the black hole at the center of our own Milky Way. Breakthroughs in cosmology, the study of universe's origins and evolution, have also been monumental. Observations of cosmic microwave background, the faint radiation left over from the Big Bang, have provided a window into an early universe. Satellites like COBE and Planck have mapped the CMB in incredible detail, offering clues about the formation of galaxies and the overall structure of the cosmos. Additionally, the discovery that the universe's expansion is accelerating, thanks to the mysterious force we call dark energy, was one of the most shocking findings in astronomy. Teams led by scientists like Saul Perlmutter and Brian Schmidt made this revelation in the late 1990s, earning them a Nobel Prize in Physics. Closer to home, our understanding of planetary science has been revolutionized by missions like Cassini and Perseverance. Cassini's 13-year exploration of Saturn and its moons revealed phenomena like the geysers of Enceladus, which spew water vapor and hint at subsurface oceans, potential habitats for life. Meanwhile, Perseverance continues to roam Mars, searching for ancient signs of life and collecting samples for eventual return to Earth. These missions have transformed our view of our neighboring worlds, emphasizing the interconnection between planetary exploration and broader astronomical research. Even in the realm of stellar evolution, breakthroughs abound. The discovery of rapid gamma-ray bursts, massive explosions from dying stars, has shed light on how stars end their lives. Such bursts, studied by satellites like SWIFT, help astronomers understand the process that generate black holes and distribute elements essential for life across the cosmos. In each of these discoveries, the contributions of astronomers and scientists are deeply intertwined. For instance, while Einstein's theories laid the groundwork for the discovery of gravitational waves, the LIGO team expanded upon his ideas with cutting-edge technology. The Event Horizon Telescope's black hole images build upon decades of research into radio astronomy and black hole physics. Astronomy thrives on this collaborative effort, where each discovery is a step forward for the entire community. These breakthroughs are not just scientific achievements, they are stories that capture the imagination, inviting us to ponder the mysteries of existence. They remind us that the universe is far more vast, complex, and extraordinary than we ever dreamed. As modern astronomy continues to push the boundaries of knowledge, one thing is clear: there are always new horizons waiting to be explored. In the ever-expanding cosmos of astronomical discovery, contemporary astronomers stand at the forefront, translating the mysteries of the universe into insights that shape our understanding of existence. Their work is a blend of curiosity, innovation, and collaboration, driven by a shared goal to unravel cosmic secrets. These individuals are not only heirs to a legacy of great thinkers, but also pioneers carving out paths to new frontiers. One of the most prominent contributors in modern astronomy is Andrea Ghez, an astrophysicist whose work has been instrumental in studying the supermassive black hole at the center of our galaxy, Sagittarius A star. Using adaptive optics and the Keck Observatory, Ghez has meticulously tracked the orbits of stars around this mysterious black hole, providing conclusive evidence of its existence. Her groundbreaking research earned her a share of the 2020 Nobel Prize in Physics, highlighting her role in uncovering some of the Milky Way's most elusive phenomena. While Ghez has illuminated the inner workings of our galaxy, another contemporary astronomer, Reinhard Genzel, has made complementary strides in the study of galactic dynamics. Genzel's pioneering infrared observations also confirmed the presence of Sagittarius A. His research not only overlaps with Gez's work, but also demonstrates how collaborative efforts between scientists can yield extraordinary results. Together, their contributions have shaped our understanding of black holes, bridging the gap between theory and observation. In the realm of exoplanet studies, scientists like Sarah Seeger have profoundly influenced our quest for alien worlds. Siga is renowned for her work on exoplanet atmospheres and habitability, often referred to as one of the foremost experts in the search for extraterrestrial life. Didier Queloz, who co-discovered the first exoplanet orbiting a Sun-like star, 51 Pegasi b, brought the study of planets beyond our solar system into mainstream astronomy. Their contributions not only complement each other, but also symbolize how diverse approaches, one focusing on atmospheric science and the other on planetary detection, can converge in the broader narrative of space exploration. Another luminary, Jocelyn Bell Burnell, has made contributions that resonate across decades. Bell Burnell's discovery of pulsars, rapidly spinning neutron stars emitting beams of radiation, altered the course of astrophysics. While her discovery dates back to the 1960s, her ongoing advocacy for diversity and inclusion in science remains vital today. Through her leadership and mentorship, Bell Burnell has inspired countless emerging astronomers, ensuring that the future of astronomy is inclusive and vibrant. Meanwhile, the contributions of citizen scientists cannot be overlooked, with platforms like Zooniverse enabling amateurs to assist in astronomical research. By analyzing star catalogs or identifying unusual cosmic phenomena, citizen scientists bridge the gap between professional astronomy and public engagement. Their efforts support contemporary astronomers in managing vast datasets, further enriching the field with diverse perspectives. Contemporary astronomers also excel in building global collaborations. For example, the Event Horizon Telescope project, responsible for capturing the first image of a black hole, epitomizes teamwork on a planetary scale. Coordinated by experts like Shep Dolman and powered by interconnected observatories, this achievement demonstrates the strength of pooling resources and expertise from around the world. The photograph of the black hole's glowing ring is not just a scientific breakthrough, it's a testament to what humanity can achieve when it works together. In addition, contemporary astronomers continue pushing boundaries with theoretical models. Priyamvada Natarajan, a theoretical astrophysicist, explores the evolution of dark matter and black holes, contributing to the intricate tapestry of cosmological research. Her work complements observational studies, tying theoretical predictions to real-world data. The interplay between observational and theoretical astronomy underscores the importance of multidisciplinary approaches. These astronomers do not operate in isolation. Their work intertwines with the engineers, programmers, and institutions supporting their endeavors. Telescope operators, data analysts, and technicians all play essential roles in facilitating discoveries. Engineers who develop adaptive optic systems, like those used by Andrea Ghez, bridge the gap between technology and science. Their contributions are an inseparable part of astronomy's progress. Contemporary astronomers are more than just researchers. They are storytellers, educators, and advocates for science. Through their efforts, they inspire curiosity in millions of minds around the globe, from school children gazing at the night sky to scholars delving into complex theories. Their work is not just about answering cosmic questions. It's about passing the torch of discovery to future generations, ensuring that the quest for understanding continues. As we celebrate their achievements, we are reminded that the cosmos belongs to everyone. Modern astronomy thrives on diversity, collaboration, and shared wonder, and the contribution of contemporary astronomers reflect that ethos. Together, they pave the way for deeper insights into the universe, keeping the flame of curiosity burning bright for all humanity. Astronomy has always had a unique ability to capture human imagination. While the field may seem like the domain of highly trained professionals with access to billion-dollar observatories, modern technology and outreach initiatives have democratized the process, enabling everyday people to contribute to significant discoveries. Citizen science has become a powerful force, bridging the gap between professional astronomers and the public, while fostering widespread engagement with the cosmos. The concept of citizen science is not new. As far back as the 18th and 19th centuries, amateur astronomers made valuable contributions to the field, from cataloging stars to discovering comets. Fast forward to the 21st century, and digital technology has transformed these amateur efforts into organized and impactful collaborations. Platforms like the Zooniverse have empowered millions of participants to help analyze astronomical data, making tasks that would take scientists decades achievable in just few years. One of the most well-known citizen science projects is Galaxy Zoo, where volunteers classify galaxies based on their shapes using data from telescopes like the Sloan Digital Sky Survey. This project has not only produced groundbreaking results, but also inspired spin-offs like Planet Hunters. In Planet Hunters, volunteers sift through light curve data from the Kepler and the TESS missions to identify exoplanets that automated systems might miss. Participants have discovered hundreds of candidate planets, demonstrating that you don't need a PhD to make significant contributions to science. Citizen scientists have also helped uncover rare and unusual phenomena. For example, Hani's Voorwerp, a peculiar glowing gas cloud near a galaxy, was first spotted by a Dutch schoolteacher, Hanny van Arkel, through Galaxy Zoo. Amateur astronomers worldwide contribute to tracking near-Earth asteroids, often acting as an early warning system for potentially hazardous objects. Beyond data analysis, public engagement in astronomy has taken on many other forms. Smartphone apps now allow users to point their devices at the sky to identify constellations, planets, and even satellites. Augmented reality and virtual reality experiences bring celestial phenomena closer than ever, enabling users to explore the surface of Mars or fly through the Orion Nebula from the comfort of their own homes. These tools not only make astronomy accessible, but also foster a sense of connection with the universe. Public events like stargazing nights, planetarium shows, and lectures further deepen this connection. Organizations such as NASA, ESA, and local astronomy clubs organize regular outreach programs to bring space science to schools and communities. Events like International Observe the Moon Night invite people from across the globe to gaze at our nearest celestial neighbor, fostering a shared sense of wonder. The contribution of citizen scientists complement the work of professional astronomers, while public engagement efforts inspire the next generation of scientists, engineers, and enthusiasts. Projects like the Zooniverse prove that science is no longer confined to labs and observatories. It is a collaborative effort that thrives on curiosity and teamwork. Citizen science and public engagement are not just changing how we do astronomy. They are reshaping who gets to participate in the quest to understand the cosmos. In this way, astronomy truly becomes a science for everyone. Modern astronomy stands on the brink of extraordinary possibilities, yet it faces challenges that threaten to hinder its progress. These obstacles, ranging from technical limitations to societal and environmental concerns, require innovative solutions and collaborative efforts to ensure that exploration of the cosmos continues to thrive. At the same time, the future prospects for astronomy are as promising as the vast universe itself. One of the major challenges in astronomy is light pollution. As urban areas grow and artificial lighting intensifies, the natural darkness of the night sky is eroded. This makes it increasingly difficult for ground-based observatories to capture faint celestial objects. Although remote locations like Mauna Kea in Hawaii or the Atacama Desert in Chile provide refuge from light pollution, there are limits to where observatories can be constructed. Efforts to combat light pollution, such as shielding streetlights or implementing dark sky policies, are vital for preserving the ability to study the stars from Earth. Another pressing challenge is the growing problem of space debris. With the proliferation of satellites and space missions, Earth's orbit is becoming crowded with inactive spacecraft, spent rocket stages, and fragments from collisions. This debris poses risk to space-based observatories like Hubble and Webb, as well as future missions. But managing the increasing congestion in orbit remains a formidable task. On a broader scale, astronomy faces funding challenges. High-tech observatories, space missions, and advanced equipment require substantial investment. Yet, budget constraints often force tough decisions. Governments and institutions must balance the cost of astronomical research with other priorities. Despite these hurdles, initiatives like public-private partnerships and crowdfunding campaigns have emerged as a creative solution to support ambitious projects. In addition to practical challenges, astronomers must grapple with the limitation of existing technology. Instruments like telescopes have pushed boundaries, but there is still much that remains beyond our reach. For instance, imaging Earth-like exoplanets with high resolution or directly observing the formation of the first galaxies will require telescopes of unprecedented scale and sensitivity. Projects like the proposed Extremely Large Telescope and LUVOIR, Large UV Optical Infrared Surveyor, aim to overcome these barriers, but their realization is years or even decades away. Despite these challenges, the future of astronomy is bright. Advances in artificial intelligence and machine learning are revolutionizing data analysis, enabling scientists to process vast datasets with remarkable efficiency. These tools are posed to uncover hidden patterns in cosmic observations, leading to discoveries that may reshape our understanding of the universe. Furthermore, the next generation of space missions promises to unveil cosmic mysteries in ways never imagined. The Nancy Grace Roman Space Telescope will complement the James Webb Space Telescope by focusing on dark energy and exoplanet research. Meanwhile, missions like the European Space Agency's Athena will delve into the high-energy universe, investigating black holes and the cosmic web. Global collaboration is also a beacon of hope for astronomy's future. Projects like the Square Kilometre Array, an international effort to build the world's largest radio telescope, exemplify the power of teamwork across nations. The SKA will explore phenomena ranging from pulsars to alien signals, showcasing what humanity can achieve when united by curiosity and ambition. As technology continues to advance, some of the most profound questions in astronomy are closer to being answered. Are we alone in the universe? What is the fate of the cosmos? And how did it all begin? The pursuit of these answers, despite the challenges, underscores the resilience and ingenuity of the scientific community. Astronomy's future isn't just about overcoming obstacles. It's about pushing boundaries, embracing collaboration, and inspiring wonder in generations to come. For all its challenges, astronomy remains a testament to the humanity's unyielding quest to understand the cosmos and our place within it. As we gaze into the infinite expanse of the cosmos, it's clear that modern astronomy represents one of humanity's most remarkable endeavors. It's a discipline that has not only expanded our knowledge of the universe, but also deepened our understanding of our own existence. From the ancient practice of charting stars with the naked eye to today's cutting-edge observatories and space missions, astronomy has always been a reflection of our curiosity, ingenuity, and determination. Through technology, we've unlocked views of the universe once thought impossible. Telescopes like JWST and Event Horizon Telescope have given us a glimpse into phenomena beyond imagination: black holes, ancient galaxies, and planets light years away. The collaborative efforts of contemporary astronomers and citizen scientists have demonstrated that this quest is not limited to a few, but belongs to us all. It's a shared journey that unites people across cultures, professions, and borders, bound by a common desire to understand the cosmos. Yet this journey is not without its challenges. Light pollution, space debris, funding constraints, and technological barriers remind us of the hurdles that we must overcome. However, the resilience of the scientific community and the unwavering support of the public ensure that solutions will be found. The history of astronomy has always been one of perseverance, turning obstacles into opportunities for growth and discovery. Looking ahead, the future of astronomy is brimming with promise. Next-generation telescopes and missions will delve deeper into the universe's secrets, answering some of our most profound questions. How did the universe begin? Are we alone in its vast expanse? What will be our ultimate destiny? The potential for groundbreaking discoveries is limitless, and each step forward reveals even more about the boundless complexity of the cosmos. Astronomy isn't just about stars, planets, or galaxies. It's a celebration of human curiosity and a testament to our ability to reach beyond our limitations. It reminds us that despite the challenges we face on Earth, there is always something greater to aspire toward. The quest to understand the universe is at its core a journey to understand ourselves. As we continue to explore the cosmos, one thing remains certain: the night sky will always inspire us to wonder, to dream, and to seek answers in the infinite expanse of space. And with every new discovery, we take one step closer to unraveling the mysteries of existence. Thank you for watching this whole series. This is the last episode of Stargazers. If you would like to watch the full series, there is a whole playlist with all 10 episodes ready for you to watch. If you enjoyed any of these videos, make sure to leave a like and subscribe to our channel to help us deliver even more cosmic videos just for you. Thank you for watching. Keep looking up.